What if everything we thought we understood about the cosmos is incomplete? What if the universe holds secrets so profound they redefine reality itself? From the invisible threads of dark matter weaving galaxies together to the mysterious push of dark energy accelerating cosmic expansion, our universe is filled with forces that defy easy explanation. We look up at the night sky and see stars, planets, and distant galaxies, but beneath that glittering surface lies a hidden architecture, an unseen framework that governs the behavior of everything from the smallest particles to the largest clusters of galaxies. These are the universe's hidden forces, and they challenge our very perception of existence. For centuries, humanity has gazed at the heavens with a mix of wonder and curiosity, trying to decipher the laws that shape our reality. Yet with every answer we uncover, new questions emerge, pulling us deeper into the cosmic unknown. Think about it, 95% of the universe is composed of matter and energy we cannot see or directly detect. That means most of what exists is fundamentally invisible to us, operating behind the scenes like the hidden mechanics of an immense cosmic clock. It's both humbling and thrilling to realize that we are only beginning to scratch the surface of understanding how the universe truly works. This isn't just about science, it's about reimagining our place in something far grander and more mysterious than we ever imagined. In this video, we're setting out on a journey to explore 30 of the most incredible theories about these hidden forces, ideas that stretch the limits of imagination and challenge the boundaries of known physics. From quantum entanglement linking particles across vast distances to the possibility of extra dimensions curled up in space, each theory offers a glimpse into a reality that is stranger and more magnificent than fiction. We'll venture into concepts that question the nature of time, gravity, and even the fabric of spacetime itself. So settle in and open your mind to the extraordinary, because what you're about to discover might just change how you see the cosmos forever. Our journey begins not with an invisible substance, but with a revolutionary tweak to a fundamental force we thought we understood. What if the mystery of galactic rotation isn't caused by something we can't see, but by a flaw in our most trusted equations? This is the bold proposition of modified Newtonian dynamics, or MOND. For decades, astronomers have observed that stars at the outer edges of galaxies orbit far too quickly to be held by the visible matter alone. According to Sir Isaac Newton's centuries-old laws of gravity, these stars should be flung out into the void, yet they remain firmly anchored. The prevailing solution has been to invoke dark matter, an invisible mass providing the extra gravitational glue. But MOND offers a strikingly different answer. Maybe our math is simply wrong for the extremely weak gravitational fields found in the outskirts of galaxies. Proposed by physicist Mordechai Milgrom in the early 1980s, MOND suggests that Newton's second law of motion behaves differently when acceleration becomes very, very small. Instead of force always equaling mass times acceleration, MOND introduces a new constant, a minimum acceleration threshold. Below this threshold, gravity effectively becomes stronger than Newton or Einstein predicted. This single adjustment to the formula does something remarkable. It accurately predicts the rotation curves of a vast array of galaxies using only their visible stars and gas. There's no need for a halo of mysterious, unseen particles. For its proponents, MOND is a more elegant solution, solving the problem without inventing an entire new form of matter that has eluded direct detection for over 50 years. The debate between MOND and the dark matter model is one of the most passionate in modern cosmology. MOND supporters point to its stunning success in predicting the motions of stars within individual galaxies, a feat that often requires fine-tuning in dark matter simulations. However, the standard model of cosmology, which includes dark matter, holds a powerful card: its ability to explain the large-scale structure of the universe. The cosmic web of galaxy clusters and the patterns seen in the cosmic microwave background are beautifully explained by the gravitational influence of dark matter. While some refined versions of MOND are attempting to tackle these larger scales, they have yet to achieve the same comprehensive success. This ongoing tug of war between a modified force and an unseen substance pushes physicists to refine their ideas, driving our understanding of gravity itself to its very limits. While MOND challenges our understanding of gravity on cosmic scales, another theory aims to rewrite the rules at the smallest levels of existence. This idea emerged not from astronomy, but from the world of theoretical particle physics, and it proposes a stunningly elegant symmetry at the heart of reality. It's called supersymmetry, or SUSY for short, and its fundamental premise is as simple as it is profound. For every known particle in the universe, there exists a hidden superpartner particle. Think of it as the universe having a hidden twin for everything we can see. For every quark, there would be a squark. For every electron, a selectron. The photon, carrier of light, would be paired with a photino. This isn't just a whimsical doubling of particles, it's a powerful mathematical framework that solves several of the most nagging problems in physics all at once. One of the biggest puzzles it addresses is known as the hierarchy problem. The mass of the Higgs boson, the particle that gives all others mass, is astonishingly fragile. Based on our current equations, quantum fluctuations should drive its value to an enormous number, making it billions of times heavier than it actually is. This suggests our math is missing a crucial piece. Supersymmetry elegantly cancels out these problematic calculations because the contributions from regular particles and their superpartners would perfectly oppose each other, leaving the Higgs mass stable and small, just as we observe. But the implications reach far beyond tidying up equations. Supersymmetry provides a perfect, natural candidate for dark matter. The lightest of these superpartners, often called the neutralino, would be stable, electrically neutral, and would only interact through gravity and the weak nuclear force. This means it could effortlessly stream through planets and people without a trace, yet clumped together in massive halos around galaxies, exactly the properties we require for a dark matter particle. Furthermore, SUSY holds the potential to achieve a grand, long-sought dream of physics, the unification of forces. At the incredibly high energies just after the Big Bang, the electromagnetic, weak, and strong nuclear forces may have all been one. Our standard model shows their strength almost, but not quite, converging at a single point. Introduce supersymmetry, and those lines snap together into a perfect meeting, suggesting a single, unified superforce at the dawn of time. The promise of this beautiful theory created immense excitement for decades, culminating in the construction of the largest machine ever built, the Large Hadron Collider. Many physicists were certain it would not only find the Higgs boson, which it triumphantly did, but also the first glimpses of these superpartners. Yet, as the collider smashed protons together at unprecedented energies, the detectors remained silent. No squarks, no photinos, no neutralinos appeared. It was a profound disappointment for the field. The simplest and most elegant versions of supersymmetry were effectively ruled out. But does this mean the theory is dead? Far from it. Theorists have not given up. The beauty and explanatory power of SUSY are too compelling to abandon outright. The thinking now is that supersymmetry might simply be broken at a much higher energy scale than we initially hoped, making the superpartners far heavier and beyond the current reach of our colliders. Or perhaps the way these particles reveal themselves is more subtle, requiring even more sensitive and indirect methods to detect their influence. The search continues, not just in particle smashers, but also in deep underground labs hunting for dark matter and in precise astronomical observations. Supersymmetry remains a brilliant, untested vision of a more complete cosmos, a testament to our enduring quest to find a deeper, more symmetric order behind the universe's apparent chaos. But what if the very fabric of space and time we inhabit is an elaborate illusion? This brings us to one of the most radical and awe-inspiring theories on our list, the holographic principle. It proposes a staggering idea: our rich, three-dimensional reality, everything you see and feel, might actually be a projection from a two-dimensional surface at the very edge of the observable universe. Think of the shimmering, three-dimensional image on your credit card. It appears to have depth and volume, but all that information is actually encoded on a flat, two-dimensional foil. The holographic principle suggests our entire cosmos might operate on a similar, albeit infinitely more complex, principle. This astonishing idea didn't emerge from pure speculation, but from a deep puzzle concerning the most destructive objects in the universe, black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's event horizon, the point of no return, has a property that behaves exactly like entropy, a measure of disorder or information. This was strange because entropy is a thermodynamic quantity, and black holes were thought to be purely gravitational. Stephen Hawking later showed that black holes aren't completely black. They slowly radiate energy and evaporate over astronomical timescales. This created a massive problem, famously known as the black hole information paradox. The laws of quantum mechanics state that information about what falls into a black hole can never be truly destroyed. But if the black hole evaporates, where does that information go? The revolutionary solution, pioneered by physicists like Gerard T. Hooft and Leonard Susskind, was that the information isn't lost at all. Instead, it is perfectly preserved, encoded on the two-dimensional surface of the black hole's event horizon. Every particle, every bit of energy that falls in, leaves an imprint on this surface, like a pixel on a vast cosmic screen. The three-dimensional interior of the black hole is in effect a projection of that data. The holographic principle takes this black hole thermodynamics and applies it to the entire universe. If a region of space with a boundary can be described by physics on its boundary, then perhaps our entire universe, which also has a kind of cosmological horizon, is a projection from a two-dimensional shell at its farthest edge. The implications are enough to make your head spin. It suggests that all the events playing out in our three-dimensional world, planets orbiting, stars burning, you watching this video, are essentially a holographic movie playing out from data stored on a distant, two-dimensional surface. It's a concept that completely inverts our understanding of reality, proposing that the fundamental, true description of the universe requires one less dimension than we experience. This isn't just a philosophical curiosity. It's a serious framework that researchers are using to tackle profound questions about quantum gravity and the fundamental nature of space itself. While it remains a highly theoretical construct, the holographic principle stands as a powerful testament to how deeply strange and wonderfully mysterious our universe may turn out to be. Now, if the holographic principle challenges the very dimensions of our reality, the next theory expands the stage of existence to an almost unimaginable degree. Imagine a single moment of choice, like deciding to turn left or right on your walk. In our experience, only one of those paths becomes real. But what if, at the most fundamental level, the universe refuses to choose? What if every single quantum possibility branches off to become its own entirely separate reality? This is the breathtaking claim of the many worlds interpretation of quantum mechanics, a vision of a limitless multiverse where every possible outcome actually happens. To understand why such a radical idea was ever proposed, we need to look at the bizarre behavior of the quantum world. In the realm of atoms and particles, things don't behave like tiny billiard balls. Instead, they exist in a fuzzy cloud of potentialities called a superposition. An electron isn't definitively here or there. It has a probability of being in many places at once. This strange state persists until the moment we observe or measure it, when it seems to instantly snap into a single, definite location. This sudden transition from possibility to reality is known as the measurement problem, and it has perplexed physicists for a century. Why does the act of observation collapse the wave function? What is special about measurement? In the 1950s, a physicist named Hugh Everett offered a stunningly simple and audacious answer: the collapse never happens. Everett proposed that the mathematics of quantum mechanics should be taken at face value. The wave function doesn't collapse because every single possible outcome contained within it actually occurs. But if all outcomes happen, why do we only experience one? Everett's answer was that we, the observers, split along with the particle. At the moment of measurement, the universe branches into multiple, non-communicating copies. In one universe, you see the electron on the left. In another, an identical version of you sees it on the right. Neither version is aware of the other. Each simply continues on in their own newly created timeline. The implications of this are staggering. Every quantum event, and there are countless trillions happening every moment, becomes a fork in the road for reality. This leads to a truly infinite multiverse where every possible history and future plays out. In one universe, a dinosaur-ending asteroid missed Earth, and you're watching this on a device built by intelligent reptiles. In another, you made a different decision years ago and live an entirely different life. The many worlds interpretation doesn't just suggest these universes exist, it demands them as a direct consequence of its equations. It solves the measurement problem by eliminating the need for a special collapse rule, presenting a vision of reality that is relentlessly and objectively real, even if most of it is forever hidden from us. Of course, a theory this grand faces fierce criticism. The most common objection is that it seems utterly untestable. If we can never interact with, observe, or receive any signal from these other branches, does the multiverse qualify as science, or is it just metaphysics? Proponents argue that its power lies in its simplicity and its ability to explain quantum weirdness without adding extra rules. They also point out that the theory makes a key prediction: the absence of true randomness. What we perceive as random quantum events are actually just us experiencing one branch of a predetermined splitting structure. The debate often spills over from physics into philosophy, forcing us to ask deep questions about the nature of reality, identity, and the meaning of probability itself. Whether you find it a beautiful explanation or an extravagant fantasy, the many worlds interpretation remains one of the most profound and mind-expanding ideas ever conceived, suggesting that our entire cosmic history is just one thread in an infinite tapestry of alternate realities. Yet if the universe truly branches with every quantum event, where does that infinite complexity ultimately reside? Our next theory offers a truly cosmic answer, proposing that the stage of reality itself is far grander and has many more layers than we ever perceived. It's called string theory, and it begins with a simple but profound shift in perspective. What if the fundamental building blocks of nature aren't tiny, point-like particles, but unimaginably small, vibrating loops of energy? For decades, our standard model of particle physics has described the universe as being made of a handful of point particles, electrons, quarks, and the like, that interact by exchanging force-carrying particles like photons. This model is spectacularly successful, but it hits a wall when it tries to incorporate gravity. The equations of Einstein's general relativity, which describe gravity as the curvature of spacetime, become riddled with infinities when applied to the quantum scale. This inconsistency suggests that a deeper, more fundamental theory is needed to unite the very large and the very small. String theory emerges as a contender for this grand unification by reimagining the foundation of everything. In this framework, every particle is not a zero-dimensional dot but a one-dimensional string, so small that it would appear as a point to any experiment we could ever devise. And just like a violin string can vibrate at different frequencies to produce distinct musical notes, these cosmic strings vibrate in specific patterns. One vibration mode makes the string appear to us as an electron, another mode makes it look like a photon, a different resonance might create a quark. In this elegant picture, the bewildering zoo of subatomic particles becomes a symphony played on these tiny strings, with each note corresponding to a different particle and its properties. Most importantly, one particular vibration pattern naturally produces a particle with the exact properties of the graviton, the hypothetical quantum carrier of gravity. For the first time, gravity is seamlessly woven into the quantum tapestry. But this beautiful idea comes with an extraordinary requirement. For the math to work, these strings cannot vibrate in just the three spatial dimensions we know. String theory demands extra dimensions of space, 6 or 7 of them, curled up into a shape so tiny and complex that they are hidden from our view. Imagine a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink yourself to the size of an ant, you would discover the hose has a second dimension, a circular cross-section, curled up into a small loop. String theory suggests that at every point in our familiar three-dimensional space, there are 6 additional spatial dimensions tightly curled into a geometric form called a Calabi-Yau manifold. The specific way these dimensions are folded determines the properties of the universe we observe, like the masses of particles and the strengths of forces. Our entire reality may be dictated by the geometry of this hidden, multidimensional landscape. The most advanced version of this idea is known as M-theory, which proposes an 11-dimensional universe where strings are just one aspect of a richer theory that also includes higher dimensional membranes, or branes for short. In this conception, our entire universe could be a 3-dimensional brane floating within a higher dimensional bulk, and the forces we feel might be confined to our brain while gravity, uniquely, could leak into the extra dimensions. This could explain why gravity is so weak compared to the other forces. It's effectively diluted across dimensions we cannot access. Yet for all its mathematical beauty and ambitious scope, string theory faces a monumental challenge, a complete lack of experimental verification. The energy levels required to directly probe these strings or uncurl the extra dimensions are far beyond the reach of any particle accelerator we could ever build. The theory makes very few concrete predictions that can be tested with current technology, leading some critics to question whether it is even a scientific theory at all or merely an exquisite mathematical exercise. Its proponents, however, argue that its profound ability to potentially unify all forces and particles into a single, coherent framework, a genuine theory of everything, makes it a pursuit worthy of the deepest investigation. A magnificent and intricate puzzle waiting for a future genius to find its final, testable form. Yet if the fundamental fabric of reality is composed of vibrating strings, one might wonder if even these strings are the final layer of existence, or if they are merely the code of a deeper, more abstract program. This leads us to one of the most provocative and debated ideas in modern thought, the simulation hypothesis. What if our universe, with all its galaxies, stars, and conscious life, isn't a purely physical system but an immensely sophisticated computer simulation, much like a hyper-realistic video game created by an advanced civilization? The argument for this astonishing possibility was formally laid out by philosopher Nick Bostrom in 2003. He presented a compelling logical trilemma, a set of 3 possibilities that he argues are nearly exhaustive. The first proposition is that almost all civilizations at our level of technological development go extinct before achieving the capability to create realistic simulations. The second is that even if they survive, advanced civilizations almost universally lack any interest in creating such simulations. Bostrom's third proposition is the punchline. If both of the first 2 are false, then we are almost certainly living in a simulation. The reasoning is based on pure numbers. If even one advanced civilization avoids extinction and develops both the capability and the desire to run ancestor simulations, high-fidelity recreations of their own past, then they would likely create a staggering number of them, perhaps billions or trillions. The vast majority of all conscious minds that ever experience a world like ours would therefore be simulated ones, not the original biological ancestors. Statistically, the odds are overwhelmingly against us being in that single, unique base reality. This argument has moved beyond philosophical circles and captured the imagination of several prominent figures in the tech world. Elon Musk has famously stated that the odds we are in base reality are 1 in billions. The reasoning is simple. 40 years ago we had Pong, 2 rectangles and a dot. Now we have photorealistic, massively multiplayer online games with millions of concurrent players, and virtual reality is becoming increasingly immersive. If this technological progression continues for even a few hundred more years, our descendants would possess the computing power to create simulations indistinguishable from reality for the simulated beings within them. The gap between our current games and a perfect simulation is vast, but it's a gap of degree, not of kind. This line of thinking naturally leads to a fascinating question. If this is a simulation, could there be glitches or shortcuts in the code that might reveal the illusion? Some have speculated that certain quantum oddities, like the way particles seem to only resolve into definite states when observed, could be a form of processing optimization. The simulation only renders the details when someone is looking to save computational resources. Others point to potential numerical constants in nature or even déjà vu as hints of a programmed reality. However, most scientists caution that these are just fun thought experiments. Any civilization capable of such a flawless simulation would almost certainly be adept at patching errors or designing a system with no detectable bugs. The most likely evidence would not be a cosmic rainbow glitch, but perhaps a deliberate message or signature left by the programmers. Beyond the scientific and logical arguments, the simulation hypothesis forces us to confront profound philosophical and ethical dilemmas. If this is a simulation, do our actions have any inherent meaning, or are we just characters in someone else's story? Would it make our suffering less real? Many philosophers argue that it changes nothing about our lived experience. Pain feels like pain, joy feels like joy, and the love we feel is no less significant whether we are made of atoms or bits. The ethical implications for the simulators, however, are immense. If they are conscious, our creators would bear a moral responsibility for the immense suffering within their simulation. This leads to dark possibilities. Perhaps they are not benevolent, or perhaps they are so advanced that our consciousness holds no more moral weight to them than a non-player character in a video game does to us. Alternatively, the simulation might be an experiment, an archival project, or even a form of entertainment. The uncertainty is both terrifying and awe-inspiring, challenging the very foundation of what we consider to be real and meaningful. But if our reality is indeed a construct, it would exist within a bounded system with limits and horizons. And at the very edge of what we can observe, astronomers have found something that challenges our understanding of those limits in an entirely different way. This brings us to a cosmic mystery known as dark flow. Imagine throwing a handful of leaves into a calm river. They would drift in various directions, carried by the local currents. Now imagine seeing every single leaf across the entire river, slowly but surely drifting in one coordinated direction. That is the baffling essence of dark flow. The discovery that not only is our universe expanding, but entire clusters of galaxies appear to be moving on a secret journey towards a single point in space, pulled by something we cannot see. This phenomenon was first detected not by looking at the galaxies themselves, but by studying the oldest light in the universe, the cosmic microwave background, or CMB. This afterglow from the Big Bang fills all of space and provides a uniform backdrop, a cosmic reference frame. Scientists using NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, realized they could use this background radiation as a measuring stick. As massive galaxy clusters move through space, the hot gas within them interacts with the CMB photons in a specific way, a subtle effect known as the kinematic Sunyaev-Zeldovich effect. This interaction creates a very slight temperature shift in the microwave background in the direction of the cluster's motion. By carefully mapping these tiny distortions for thousands of clusters, researchers led by Alexander Kashlinsky made an astonishing discovery. These clusters, scattered across billions of light years, were not moving randomly. They displayed a coherent collective velocity, streaming at speeds of over 600 miles per second toward a specific region in the constellations Centaurus and Vela. This motion is in addition to the overall expansion of the universe. It's a directional flow on a truly colossal scale. The most staggering implication is the proposed cause. The gravitational pull required to move thousands of galaxy clusters must be unimaginably vast, a structure of such immense mass and size that it defies comprehension. The problem is, this gravitational source cannot be within our observable universe. If it were, we would see it. This suggests that the source of the pull lies beyond our cosmic horizon, in a region of space-time from which light has not had time to reach us since the beginning of the universe. It hints at a pre-Big Bang reality, a larger cosmic structure of which our universe is only a part. One radical possibility is that it's the gravitational tug of a neighboring universe in a vast multiverse, a concept that moves from theoretical speculation into the realm of potential observational evidence. Unsurprisingly, a claim this extraordinary faces intense scrutiny and skepticism from the cosmological community. The primary criticism centers on the data itself. The measured signal is incredibly faint, sitting right at the edge of what our instruments can detect. Some analyses of data from the more precise Planck satellite have failed to confirm the dark flow signal with the same strength, suggesting that the initial findings might be contaminated by unknown systematic errors or foreground emissions within our own galaxy that weren't fully accounted for. Critics argue that until the signal is unambiguously confirmed with future, even more sensitive telescopes, it remains an intriguing but unproven anomaly. The debate continues, a tense standoff between a potentially universe-shattering discovery and the relentless standards of scientific proof. Whether a confirmed reality or a cosmic mirage, dark flow forces us to confront the humbling possibility that the greatest structures and forces in existence may lie forever beyond our view, silently shaping the destiny of everything we can see. But what if the story of our universe isn't a one-time epic with a definitive beginning, but merely the latest chapter in an infinite cosmic cycle? This brings us to a profoundly different vision of cosmic origins known as the Big Bounce. While the standard Big Bang model posits a singular, absolute beginning from an infinitely dense point, the Big Bounce theory suggests our expanding universe was born from the collapse of a previous one. Instead of a definitive genesis, we have an endless rhythmic dance of expansion and contraction, a great cosmic inhale and exhale stretching across eternity. The primary motivation for this cyclical model is to solve one of the most intractable problems in physics, the initial singularity. The Big Bang theory tells us that the entire universe was once compressed into a point of infinite density and temperature, where the known laws of physics simply break down and offer no answers. A singularity represents a frontier beyond which science cannot currently go, a place where gravity becomes so strong that quantum effects must dominate, yet we lack a theory of quantum gravity to describe it. The Big Bounce elegantly sidesteps this problem. In this scenario, the universe never reaches a true point of infinite density. Instead, the gravitational collapse of a previous universe is halted and reversed by a powerful repulsive force arising from quantum effects, creating a rebound, a bounce, that births a new expanding universe. This isn't just a philosophical idea. It finds potential support in a leading candidate for a theory of quantum gravity called loop quantum gravity, or LQG. Unlike string theory, which adds extra dimensions, LQG attempts to quantize spacetime itself, describing it as a fabric woven from tiny, discrete loops. This approach provides a concrete mechanism for the bounce, as the previous universe contracts towards what would be a singularity in classical physics. The quantum nature of spacetime in LQG resists further compression. The density reaches a tremendous but finite maximum, and the repulsive quantum force generated at this peak becomes so powerful that it overwhelms the pull of gravity, causing the universe to rebound into a new phase of expansion. It's akin to compressing a spring to its absolute limit. The potential energy stored becomes immense, forcing it to spring back with incredible force. This breathtaking vision naturally leads to a pressing question about our own universe's fate. We have observed that the expansion of the cosmos is not slowing down but accelerating, driven by the mysterious force of dark energy. If the universe is flying apart faster and faster, destined for a cold, empty end in a big freeze, how could it ever reverse course into a big crunch to set up the next bounce? Proponents of the cyclical model have developed answers. Some theories suggest that the nature of dark energy could change over trillions of years, its repulsive force weakening and eventually allowing gravity to regain dominance. Alternatively, the universe might not need to fully contract everywhere. A bounce could be a more local phenomenon within a larger multiverse framework, or our understanding of dark energy might be incomplete. While the accelerating expansion presents a significant challenge, it hasn't definitively ruled out the possibility of a future cosmic turnaround, leaving the door open for this majestic and timeless view of existence. But what if our universe wasn't born from a bounce or a bang, but from a cosmic collision? This brings us to a truly mind-bending alternative rooted in the higher dimensions of string theory, the ekpyrotic universe model. The name itself comes from the Greek word for conflagration or fire, but this is a very different kind of fire than the Big Bang's explosive beginning. Instead of a singularity, this theory proposes that our entire three-dimensional existence was forged in a slow, violent crash between two parallel worlds. To understand this, we need to return to the concept of brains from M-theory. Imagine our universe is not all there is, but is instead a single three-dimensional membrane, or brain, floating within a higher dimensional space called the bulk. Now picture another flat, three-dimensional brain, a parallel universe floating on a parallel course in this bulk. For most of eternity, these two brains drift along, empty, cold, and static. But gravity, which is not confined to the brains, acts between them, slowly pulling them closer together over an almost unimaginable timescale. They don't rush toward each other. It's a gradual, inevitable drift. When they finally collide, the energy of that impact is not an explosion from a point, but a wave of creation that ripples across the entire surface of our brain. This wave is the ekpyrotic event, and it fills our newborn universe with the hot, dense plasma of matter and radiation we identify as the Big Bang. In this view, the Big Bang wasn't the beginning of everything, but merely the dramatic moment our local region of spacetime was heated up and set into motion. One of the most compelling advantages of this model is its elegant solution to a major problem the standard Big Bang theory struggles with: the horizon problem. Our observable universe is incredibly uniform. The temperature of the cosmic microwave background is the same in all directions to within 1 part in 100,000, meaning regions on opposite sides of the sky, which could never have been in thermal contact according to standard cosmology, are mysteriously identical. The prevailing solution is a period of hyper-fast expansion called inflation, which blew up a tiny, uniform patch to become our entire cosmos. The ekpyrotic model offers a very different explanation. Because the colliding brains are flat, cold, and nearly featureless for eons before the collision, they have an immense amount of time to settle into a state of equilibrium and uniformity through interactions across the bulk. When they finally collide, that inherent uniformity is imprinted directly onto the new, hot universe. The entire surface of the brain starts off with the same conditions simultaneously, eliminating the need for a separate, ad hoc inflationary period. The key to testing this incredible idea may lie in the faintest ripples in spacetime itself, primordial gravitational waves. These are ripples predicted to have been generated in the universe's very first moments, and their specific signature would act as a fingerprint of the mechanism that created them. The standard inflationary model predicts that these waves would leave a very distinct and strong pattern on the polarization of the cosmic microwave background. The ekpyrotic scenario, however, makes a different prediction. The slow, gradual collision of the brains is a much gentler process than the violent, exponential energy surge of inflation. As a result, it would produce a spectrum of gravitational waves that is exponentially weaker and possibly entirely undetectable by our current observatories. Therefore, the ongoing, meticulous search for these primordial waves isn't just about confirming inflation. It's a potential arbiter between these two vastly different origin stories. If next-generation telescopes finally detect the strong signal inflation predicts, it would be a major blow to the ekpyrotic model. But if they continue to find nothing and the silence persists, it would make the case for a colliding brain universe significantly stronger, pointing toward a cosmic genesis not of fire but of impact. What if one of the most sacred constants in all of physics, the very backbone of Einstein's relativity, wasn't always so constant? Our next theory dares to ask exactly that, proposing a revision so radical it challenges the core of modern cosmology. This is the idea of a variable speed of light, or VSL. The speed of light in a vacuum, denoted by the letter c, is enshrined in physics as an immutable universal speed limit, approximately 186,000 miles per second. It's the c in E equals mc squared, the fundamental conversion factor between space and time. But what if, in the extreme heat and density of the universe's first moments, light itself raced across the newborn cosmos at a vastly different, far faster pace? This provocative idea didn't emerge from nowhere. It was developed as a direct competitor to the leading theory of the universe's early moments, cosmic inflation. Remember the horizon problem we discussed earlier, the puzzle of how regions of space too far apart to have ever communicated somehow share the same temperature and properties. Inflation solves this by proposing a period of faster-than-light expansion that blew a tiny, uniform patch into our entire cosmos. But some physicists like Joe Megiddo and John Moffat wondered if there might be a more straightforward solution. Instead of space expanding unimaginably fast, what if light simply traveled faster, allowing distant regions to communicate and thermalize before settling down to the speed we observe today? In this VSL scenario, the horizon problem vanishes because information and energy could crisscross the entire infant universe almost instantaneously, creating the uniformity we see. The theory also tackles another major issue, the flatness problem. Our universe appears incredibly flat on large scales, meaning its geometry adheres to the classic rules of Euclid, with parallel lines never meeting. The standard Big Bang model requires that the initial expansion was fine-tuned to an astonishing degree of precision, like balancing a pencil on its tip for billions of years to achieve this outcome. A faster speed of light in the early universe alters the equations governing this expansion, acting as a natural attractor that drives the cosmos toward flatness without any need for miraculous fine-tuning. It's an elegant alternative that achieves the same explanatory goals as inflation but through a completely different, and for some more intuitive, mechanism. Of course, tampering with a foundation stone of physics like C is not done lightly, and the VSL hypothesis faces monumental challenges. The entire edifice of Einstein's special relativity is built on the assumption of a constant speed of light. Changing c doesn't just affect light, it ripples through all of physics, potentially altering the strengths of fundamental forces, the behavior of particles, and the very relationship between cause and effect. Proponents of VSL have worked to develop new, self-consistent mathematical frameworks where the variation occurs in a way that preserves the most important laws and doesn't lead to logical paradoxes. They suggest that this variation could be tied to the energy scale of the universe, with the speed of light locked into its current value as the cosmos cooled, much like water freezing into ice. The primary hurdle for VSL, beyond its theoretical upheaval, is a lack of definitive experimental evidence. While it makes predictions that differ from inflation, particularly regarding the pattern of ripples in the cosmic microwave background, current observational data from telescopes like Planck is precise enough to rule out some simple versions of VSL, yet not precise enough to confirm the more sophisticated models. For now, inflation remains the dominant paradigm because it is better integrated into the larger tapestry of particle physics. Yet, the persistence of the VSL idea highlights a fascinating aspect of scientific progress: the value of heretical challenges to orthodoxy. Even if it never supplants inflation, the work on variable speed of light pushes cosmologists to test their assumptions more rigorously and to consider whether the constants we hold dear are truly constant, or if they are merely the frozen parameters of our current cosmic epoch. But if the speed of light itself might be a variable in the cosmic equation, it forces a much deeper and more philosophical question: why do any of these fundamental constants have the precise values they do? Why is the force of gravity so exquisitely balanced, or the mass of the electron so perfectly set, that stars can shine and planets can form and life can eventually emerge? This line of inquiry leads us directly to one of the most profound and debated principles in all of modern science, the anthropic principle. In its simplest form, it suggests that the universe's constants are finely tuned for life for the straightforward, almost tautological reason that we are here to notice. If they weren't, we wouldn't exist to ponder them in the first place. This idea is often broken down into two distinct versions, each with escalating implications. The weak anthropic principle is a statement of observational selection bias. It notes that we must find ourselves in a universe capable of sustaining life, because that's the only kind of universe where observers can arise. It's a logical constraint, not an explanation. Think of a puddle waking up one morning and marveling at how the hole it resides in fits its shape so perfectly. The puddle might conclude the hole was designed specifically for it, when in reality, it's simply the only hole in which a puddle could form. Similarly, we find ourselves in a universe with the right conditions for life, not necessarily because it was made for us, but because we are a product of those conditions. It's a cosmic version of survivorship bias. Then there's the far more radical strong anthropic principle. This version moves beyond a simple statement of fact into a much more contentious claim, that the universe must have those properties which allow life to develop at some stage in its history. The word must is doing a lot of heavy lifting here, implying some form of necessity or even design. This interpretation often veers into the theological or metaphysical, suggesting the existence of a universe-generating mechanism that is constrained to produce life-permitting worlds or even a conscious goal. It's a principle that makes many physicists deeply uncomfortable because it can feel like it halts scientific inquiry, replacing a search for mechanism with a kind of philosophical shrug. However, modern cosmology has provided a powerful and more scientific framework that gives the anthropic principle real explanatory teeth: the multiverse. If an enormous, perhaps infinite, ensemble of universes exists, each with its own random set of physical constants and laws, then it is no longer surprising that we find ourselves in one of the exceedingly rare universes where those constants are just right for life. In this vast cosmic lottery, we hold the winning ticket not because the lottery was fixed, but because every possible combination was tried. The multiverse transforms the anthropic observation from a curious coincidence into a statistical inevitability. We don't need to explain why our constants are perfect. We only need to explain that in a sufficiently large multiverse, a universe like ours was bound to appear by pure chance. This perspective offers a potential answer to the puzzle of dark energy. Its observed value is absurdly small and seems unnaturally fine-tuned. If it were even slightly larger, the universe would have expanded too rapidly for galaxies to ever form. If it were much smaller, the cosmos might have collapsed back on itself long before life could evolve. In a multiverse, this isn't a problem. Most universes have a dark energy value that makes them barren and empty, but a tiny fraction, by pure random chance, get the number just right. We, of course, can only exist in that lucky fraction. The anthropic principle, coupled with the multiverse, doesn't just explain our existence. It predicts that we should observe a value for dark energy that is small enough to allow galaxy formation, but not zero, a prediction that aligns remarkably well with our actual measurements. Yet, this application of anthropic reasoning is not without its fierce critics. Some argue that it is a slippery slope, a theory of anything that can explain everything and therefore predicts nothing. If any value for a constant can be explained away by saying, well, it had to be that way for us to exist, then have we truly explained anything at all? Others find the entire concept of an unobservable multiverse to be unsatisfactory, a retreat from the traditional goal of physics to find a unique, compelling, and fundamental theory that explains why our constants must have the values they do, not just how we got lucky. The debate ultimately strikes at the heart of the scientific method itself, forcing us to ask what constitutes a good explanation and whether the ultimate nature of reality might include elements forever beyond our empirical grasp. Whether one sees it as a profound insight or a philosophical cop-out, the anthropic principle remains an inescapable part of the conversation about our universe's most fundamental rules, a constant reminder that the act of observation is inextricably linked to the reality we seek to understand. But what if the very act of observation that defines a reality also dictates its continuity for the observer? This leads us to a deeply unsettling and profoundly personal twist on the many worlds interpretation, a thought experiment that ventures from the abstract into the intimately terrifying. It's called quantum immortality, and it proposes a dark corollary to the endless branching of realities. Your conscious experience might be inextricably tied to timelines in which you do not die. To grasp this, let's return to Schrödinger's famous cat, both alive and dead in its box until observed. The many worlds interpretation says that at the moment the box is opened, the universe splits. In one branch, you see a living cat and feel relief. In another, a version of you sees a dead cat and feels grief. Now, apply that same logic to yourself in a life or death scenario. Imagine you reluctantly participate in a macabre version of Russian roulette. You place a single bullet in a revolver's 6 chambers, spin it, point it at your head, and pull the trigger. In that moment, according to quantum mechanics, the outcome is a superposition, a probability of life and a probability of death. When the trigger clicks, the universe is thought to split. In most branches, 5 out of 6, you hear a harmless click and live, but in one branch, the gun fires. From the perspective of an outside observer, this is a tragedy. They will witness your death in that one timeline and mourn you. But from your perspective, a bizarre thing happens. You can only experience the timelines in which you are conscious. If the gun fires, your conscious experience in that branch ends instantly. You are not around to experience the outcome of your own death. Therefore, from your first-person point of view, you will always hear the click. No matter how many times you spin the chamber and pull the trigger, your conscious awareness will seemingly defy the odds, consistently finding itself in a world where you survive the attempt. It would appear to you as if you are miraculously lucky, even immortal, while from the outside, most versions of you have perished. This isn't just a parlor trick with probability. It ventures into some of the most disorienting philosophical territory imaginable. It forces us to ask what we even mean by self. Is there a single continuous you, or are you a different, slightly altered version in each branching timeline? The theory suggests that your stream of consciousness isn't a thread moving through a single reality, but a path that only travels along the branches of the multiverse tree where your existence continues. This leads to truly bizarre conclusions. An advocate of this idea might argue that no one ever dies of old age in their own experience. From your subjective viewpoint, you might always find yourself surviving against all odds, living through wars, accidents, and illnesses, eventually becoming the oldest person alive in your reality, while countless other versions of you succumbed long ago. You would witness everyone around you dying, seemingly at random, while you persist, not through any special quality, but simply because the branches where you die are subjectively unobservable to you. The ethical implications are a rabbit hole of their own. If this theory were true, and it's crucial to remember it is a thought experiment, not established fact, it could potentially be used to justify incredibly reckless behavior. Someone might think, why not play the odds? My consciousness will just jump to a timeline where I succeed. This is a dangerous and profound misunderstanding. In the vast majority of branches, that action would result in your death, leaving behind grief and chaos. Your experience would simply end in those branches. There is no jumping for a unified self. The you that continues would be a version that got lucky, not a soul transferring between worlds. It's a theory that speaks to the nature of experience, not a guide for living. Ultimately, quantum immortality is less a scientific hypothesis and more a profound meditation on consciousness, identity, and the haunting possibility that our personal reality is far stranger and more selective than we could ever have imagined. But what if a structure could defy one of the most fundamental principles in all of science, not by moving through space, but by moving through time itself? This brings us to a form of matter so strange it was once thought impossible, the time crystal. In our everyday experience, we're familiar with the three classic states of matter: solid, liquid, and gas. We also know about more exotic phases like plasmas or Bose-Einstein condensates, but all of these exist in a state of equilibrium, and they all obey a fundamental rule: the laws of physics are symmetric in time. This means that an experiment should yield the same result whether you run it today, tomorrow, or a billion years from now. The time crystal shatters this expectation. It's a quantum system that achieves a stable, repeating pattern of motion in its lowest energy state, effectively breaking time translation symmetry. In simpler terms, it's an object that oscillates, rotates, or changes in a periodic cycle forever, without ever consuming any energy. The theoretical foundation for this bizarre idea was laid by Nobel laureate Frank Wilczek in 2012. He pondered whether a system could be, in its ground state, the state of absolute zero energy where nothing is supposed to happen, and still exhibit motion. It sounded like a recipe for a perpetual motion machine, which thermodynamics explicitly forbids because it would create energy from nothing. But Wilczek's insight was more subtle. A true time crystal doesn't output energy, it doesn't do any work. Instead, it's a system that is perpetually in motion without any energy loss or input, a bit like a superconductivity for motion rather than electrical current. The key is that its motion is not driven by energy. It's an inherent, unchangeable property of its quantum ground state. This makes it a non-equilibrium phase of matter, a category that simply didn't exist before. Of course, proposing such a thing immediately sparked fierce debate and skepticism within the physics community. Many argued it was fundamentally impossible, a violation of cherished physical laws. The path to resolution came from refining the definition. researchers realized that for a time crystal to be physically possible, it couldn't be a closed, isolated system completely cut off from the universe. The breakthrough came with the concept of a floquet time crystal or a discrete time crystal. In this setup, the system is periodically kicked or driven by an external laser or microwave pulse, which provides a tiny amount of energy to initiate the cycle. The magic happens in the response. In a normal system, the rhythm of its motion would exactly match the rhythm of the external kicks. But in a time crystal, the system establishes its own, slower rhythm. It might oscillate once for every 2 kicks, a phenomenon known as subharmonic response. Crucially, this rhythm is incredibly robust and stable against disturbances, a hallmark of a true phase of matter. The experimental race was on, and in 2017, 2 teams, one at Harvard and one at the University of Maryland, announced they had created the first working time crystals. The Maryland team used a line of 10 ytterbium atoms whose spins were manipulated with lasers. The Harvard team used a dense cloud of nitrogen vacancy centers within a diamond. In both cases, they observed the telltale signature, a persistent subharmonic oscillation that remained locked in and stable even as they introduced noise into the system. It wasn't a perpetual motion machine, but it was a stunning validation of a new phase of matter that exists in a never-ending dance through time. The implications of this discovery stretch far beyond a laboratory curiosity. The most promising application lies in the field of quantum computing. One of the biggest hurdles for building a practical quantum computer is decoherence, the tendency of fragile quantum states to collapse due to the slightest interaction with their environment. Qubits, the fundamental units of quantum information, are notoriously error-prone. The incredible stability and coherence of a time crystal's periodic motion could provide a solution. Researchers envision using time crystals as perfect, self-correcting quantum memories or as ultra-stable clocks to synchronize operations within a quantum computer, effectively creating a protected environment where quantum information can survive for dramatically longer periods. While still in its infancy, this potential could be the key that unlocks the true power of quantum technology, all thanks to a form of matter that has forever changed our understanding of motion and time. Yet if time itself can be made to crystallize into a stable, repeating pattern, it forces us to confront a far more fundamental mystery at the edge of a black hole, where time is thought to stretch and distort into nothingness. This brings us to one of the most intense and long-running debates in all of theoretical physics, the black hole information paradox. At its heart, this is a direct conflict between the 2 great pillars of modern physics: the deterministic, smooth geometry of Einstein's general relativity and the probabilistic, never-forgetful world of quantum mechanics. The question is devastatingly simple. When something falls into a black hole, is the information about what it was truly destroyed, erased from the universe forever? To understand the gravity of this problem, we first need to understand what physicists mean by information. This isn't about books or hard drives. In quantum mechanics, information refers to the specific quantum state of every particle, its precise mass, charge, spin, and position. The fundamental tenet of quantum theory is unitarity, the principle that information is never, ever lost. It can be scrambled, spread out, and become incredibly difficult to read, like shredding a document and throwing the confetti into a hurricane. But in principle, every single shred still exists. If you had a perfect computer and knew the laws of physics, you should be able to run the universe backwards and reconstruct exactly what fell into that black hole. This preservation of information is the bedrock of quantum physics. Now enter Stephen Hawking. In the 1970s, he made his famous discovery that black holes aren't completely black. Due to quantum effects at the very edge of the event horizon, they slowly emit a faint glow of radiation, now known as Hawking radiation. This radiation allows the black hole to gradually lose mass and, over astronomical timescales, completely evaporate, disappearing from the universe. Here's the problem. Hawking's calculations showed that this radiation is entirely thermal, random, and featureless. It's pure heat, like the glow from a stove burner. It contains no information whatsoever about the particular star, book, or cat that originally fell in. So, if the black hole evaporates into a cloud of random radiation and vanishes, what happened to the immense amount of quantum information it swallowed? Hawking's terrifying conclusion was that it must be irrevocably destroyed. He famously proclaimed that this meant even God's rulebook was incomplete, and he bet against the preservation of information. This declaration sent shockwaves through the physics community because it meant one of our two foundational theories had to be wrong. Either general relativity was incorrect in its prediction of Hawking radiation, or quantum mechanics was wrong about the absolute preservation of information. For decades, this was the stalemate. The breakthrough, as we touched on with the holographic principle, came from realizing that the information wasn't inside the black hole or lost with it. Instead, it was somehow encoded on the black hole's two-dimensional event horizon, the ultimate cosmic scratchpad. The three-dimensional interior, with all its contents, is a projection of that data. When Hawking radiation is emitted, it subtly interacts with and carries away imprints of this encoded information, like smoke carrying the scent of what is burning. The information is never truly lost. It is just horrifically scrambled and nearly impossible to decode. Hawking eventually conceded this point, paying off his bet and admitting that information does, in fact, escape. But just as that solution seemed to settle the dust, it unleashed an even more violent storm known as the firewall paradox. If information is slowly leaking out in the Hawking radiation, it forces a dramatic choice about what happens to an astronaut falling into the black hole. Quantum mechanics requires something called entanglement. Particles of Hawking radiation are entangled with each other. But for the information to be transmitted out, the late-time radiation must also become entangled with the early radiation. The mathematical rules of quantum mechanics state that a particle cannot be fully entangled with two different things at once, a rule called monogamy of entanglement. To resolve this, physicists Ahmed Olmary, Donald Marolf, Joe Pulczynski, and James Sully argued that the entanglement must be violently broken at the horizon. This breaking would release a cataclysmic amount of energy, meaning the event horizon would not be an empty, smooth space as relativity predicts, but a searing wall of fire, a firewall, that would instantly incinerate any infalling object. This is the paradox in its most extreme form. Now you have a direct contradiction at the event horizon itself. From the perspective of an astronaut falling in, general relativity insists she should feel nothing special as she crosses the horizon. It's just empty space. But quantum mechanics, in its effort to save information, seems to demand that she be vaporized by a firewall. So, which is it? Does relativity fail, meaning black holes don't have an interior, or does quantum mechanics fail in its treatment of entanglement? The firewall paradox is so jarring because it shows that our two most successful theories are not just mildly inconsistent when pushed to their limits, they are screaming at each other, offering mutually exclusive versions of reality. Resolving this paradox isn't just an academic exercise for physicists. It is considered the single most important stepping stone toward a theory of everything, a theory of quantum gravity. Whoever can successfully explain what happens at the edge of a black hole will have found the key to unifying the force of gravity with the quantum world, finally creating a single framework that describes all of nature's laws. The solutions being proposed are as wild as the paradox itself, from the ER=EPR idea that black holes are connected by wormholes to their own radiation, to the finality of the firewall itself. Each potential answer forces us to radically redefine our understanding of space-time, information, and the very nature of reality. making the black hole information paradox the ultimate crucible where our future understanding of the universe will be forged. But if the information falling into a black hole creates a paradox about reality's consistency, our next theory questions the very nature of our own existence in the most unsettling way imaginable. This is the thought experiment of the Boltzmann brain, and it presents a statistical nightmare that emerges directly from our deepest cosmological theories. It proposes a chilling possibility that you, with all your memories and sense of a continuous life, are not the product of billions of years of slow cosmic evolution, but are instead a momentary and accidental fluctuation, a fully formed brain that has spontaneously assembled from random particles in the void, complete with a full set of entirely false memories. The idea finds its roots in the 19th century work of physicist Ludwig Boltzmann, who grappled with the concept of entropy and the arrow of time. He suggested that in an eternal and infinitely large universe, even the most incredibly improbable events must eventually happen given enough time. The most likely state of the cosmos is one of maximum entropy, a featureless, lukewarm soup of particles where nothing interesting ever occurs, a state known as thermal equilibrium. But within that vast, dead equilibrium, random quantum fluctuations can cause particles to momentarily arrange themselves into ordered structures. Most of these fluctuations are tiny and insignificant. But given an infinite amount of time, even the most complex and ordered system, like a planet or a living brain, could theoretically pop into existence by pure random chance. This leads to a devastating statistical argument. Which is more probable, the incredibly long and convoluted sequence of events required to form an entire universe, wait billions of years for galaxies and solar systems to coalesce, evolve life on a planet, and eventually produce your conscious mind? Or the far simpler event of a single, self-aware brain fluctuating into existence for just a few seconds, complete with the illusion of having lived in such a universe? The mathematics of probability suggests the latter is vastly more likely. In an eternal, empty universe, the number of these random, Boltzmann brains should, statistically speaking, far exceed the number of real, biologically evolved brains. Therefore, if our current cosmological models are correct and the universe is destined for an eternal heat-death, then you are almost certainly not who you think you are. You are a fleeting accident, a cosmic misfire that will almost instantly dissolve back into the chaos from which it came. The implications of this are profoundly disturbing for physics and philosophy alike. It completely undermines the principle of induction, the foundation of all scientific reasoning, the idea that our past observations reliably inform us about the future. If all your memories and scientific data are just a random, temporary glitch, then you have no reason to believe the laws of physics will hold true in the next moment. The entire scientific enterprise, built on the consistency of nature, collapses into absurdity. Furthermore, it creates a bizarre observational paradox. Our universe is clearly not in a state of thermal equilibrium. It is filled with complex, low-entropy structures like stars and galaxies. The standard explanation is that it started in a very special, highly ordered low-entropy state, the Big Bang. But if Boltzmann brains are more probable, then the most common observer should be one that hallucinates a universe from the void, not one that exists in a real, structured cosmos. The fact that we observe a coherent, ancient universe is itself powerful evidence against the cosmological models that predict our reality should be overrun by these phantom minds. For these reasons, most physicists actively hope the Boltzmann brain scenario is not true, and they use its absurd conclusion as a litmus test for the validity of our cosmological models. If a theory, like an eternally inflating multiverse or a universe with a positive cosmological constant destined for eternal heat-death, predicts that Boltzmann brains should dominate, then that theory is likely flawed or incomplete. The thought experiment thus acts as a powerful constraint, pushing cosmologists to search for models that avoid this eerie fate. perhaps by suggesting our universe is not eternal or will eventually experience a big crunch that resets the entropy clock. The Boltzmann brain remains one of the most disquieting ideas in all of science, not because anyone believes it is real, but because it forces us to confront the deepest assumptions about reality, causality, and our own fragile place in a potentially infinite and chaotic cosmos. What if the very idea of a particle is too limiting? Our journey into the hidden architecture of the universe now takes us to a theory so radical it proposes an entirely new form of matter, one that doesn't even behave like matter as we know it. This is the world of unparticle physics, a concept introduced by physicist Howard Georgi that challenges one of our most fundamental assumptions, that everything is made of distinct quantized particles. To grasp this, we need to understand scale invariance. In our everyday world, scale matters. A mountain is not just a big rock, its properties change with its size. But some systems look the same no matter how much you zoom in or out. A classic example is a fractal pattern, like a snowflake or a fern, where the same intricate structure repeats at every level of magnification. Georgi asked a profound question: what if a hidden sector of reality governed by an unparticle field possesses this exact property of scale invariance? In this realm, there would be no fundamental units, no indivisible building blocks. Instead, this unparticle stuff would behave more like a continuous, holistic substance. It wouldn't manifest as discrete particles with specific masses. It would appear as a sort of ethereal, non-particulate stuff that doesn't fit into our standard catalogue of matter. So how would this bizarre substance reveal itself? The most promising arena is within the colossal particle colliders like the Large Hadron Collider. When physicists smash protons together, they meticulously account for the energy of all the debris that comes flying out. The golden rule is that energy must be conserved. The energy going into the collision must equal the energy of all the detected particles coming out. But imagine a scenario where two protons collide and a shower of known particles is detected, yet a significant amount of energy seems to have simply vanished. This is a missing energy signature, and it's a classic hallmark of something invisible escaping the detector. While this is also a telltale sign of dark matter, unparticles would create a unique and startling pattern in the data. The missing energy wouldn't look like it was carried away by a single, heavy particle. Instead, it would appear as if it was taken by something that behaves like a fractional number of invisible particles, a statistical ghost that defies simple counting. This strange signal would be the fingerprint of scale-invariant unparticle stuff interacting with our world. This theory's potential connection to dark matter is what makes it especially compelling. Dark matter, as we've discussed, must be stable, electrically neutral, and only interact weakly. Certain types of unparticle fields could perfectly fit this description. They wouldn't clump together like individual particles, but could instead form a smooth, continuous halo around galaxies, providing the gravitational scaffolding we observe. This offers a fascinating alternative to the WIMP paradigm, suggesting that dark matter might not be a particle at all, but a pervasive, scale-invariant substance that permeates the cosmos. It's a concept that pushes the boundaries of what matter can be, forcing us to consider that the true nature of reality might be far more fluid and interconnected than our particle-based models suggest. While still a speculative idea, unparticle physics stands as a testament to the creativity of theoretical physics, constantly inventing new languages to describe the profound and hidden truths of our universe. What if gravity, the force that sculpts galaxies and holds our feet to the ground, isn't a fundamental force at all? What if it's merely a side effect, an illusion stemming from something far more primitive? This is the breathtaking and controversial proposition of emergent gravity, a theory put forward by Dutch theoretical physicist Erik Verland. In this radical view, gravity is not a force to be quantified and added to the other fundamental interactions. Instead, it emerges spontaneously from the universe's need to process information, much like the concept of temperature emerges from the frantic motion of molecules. Verlin's idea builds directly upon the holographic principle we explored earlier. Recall that the principle suggests the information describing a three-dimensional volume of space can be thought of as encoded on its two-dimensional boundary. Verlin takes this a step further by applying the laws of thermodynamics to this cosmic information screen. He asks a profound question: what happens when you add a new piece of matter to a region of space? That new mass carries with it its own information, its own entropy. According to Verlin, the holographic screen must adjust to accommodate this new data, and it's that process of adjustment, that elastic response of spacetime itself, that we perceive as the attractive force of gravity. In essence, gravity is the universe's way of rebalancing its books, of maximizing its entropy in response to a change. The most stunning consequence of this framework is its potential explanation for dark matter. Remember the galactic rotation problem that MOND and dark matter both attempt to solve. Verlin's theory naturally produces a MOND-like behavior without needing to modify Newton's laws or invoke invisible particles. In his equations, the extra gravitational pull in the outskirts of galaxies isn't caused by dark matter, but is instead a result of what he calls dark energy. In the sparse regions between galaxies, dark energy dominates, and Verlin calculates that its presence, combined with the entropy-based nature of gravity, creates an additional gravitational effect. This effect precisely mimics the presence of a dark matter halo. In this view, dark matter isn't a substance, it's a manifestation of the interaction between the universe's information content and the underlying dark energy. Unsurprisingly, a theory this paradigm-shifting has received a deeply mixed reception. Many physicists hail it as a brilliant and deeply creative approach that could finally unify gravity with quantum mechanics through an entirely new pathway. They see it as a potential leap beyond our current stuck models. However, critics point to significant challenges. The mathematics of emergent gravity is incredibly complex and some argue not yet fully developed to the point where it can make precise, testable predictions that differ from the standard dark matter model across all astronomical scales. While it works remarkably well for individual galaxies, its success in explaining the dynamics of entire galaxy clusters or the intricate patterns of the cosmic microwave background is still a subject of intense debate and ongoing calculation. The ultimate verdict will come from observation. Astronomers are now putting emergent gravity to the test. One key method involves studying the gravitational lensing of light around galaxies, how their gravity bends the light from objects behind them. The dark matter model predicts a specific lensing pattern based on the distribution of invisible mass. Verlin's theory predicts a slightly different pattern, one dictated by the entropy-based equations. By using incredibly precise telescopes to map the distortion of light around thousands of galaxies, scientists are essentially conducting a direct showdown between particles and information. The early results are intriguing but inconclusive, with some studies showing a better fit for dark matter and others suggesting the data is at least consistent with Verlin's ideas. Whether it ultimately proves correct or not, emergent gravity has already achieved something vital. It has forced the physics community to question its most basic assumptions about the nature of force and matter, opening a daring new front in our centuries-long quest to understand gravity. Yet if a black hole represents a one-way door into oblivion, what would its ultimate opposite look like? This brings us to a concept that seems ripped from the pages of the wildest science fiction, the white hole. In the stark simplicity of Einstein's equations for general relativity, the mathematics that describes a black hole is time-symmetric. This means if you were to take the equations and literally reverse the direction of time, you would get a perfectly valid, albeit bizarre, new solution. A black hole is defined by an event horizon from which nothing can escape. A white hole, therefore, would be a region of space-time from which nothing can enter. It wouldn't be a cosmic vacuum cleaner, but a cosmic fire hydrant, a point of no entry where matter and energy violently and continuously erupt outward into the universe. The theoretical possibility of white holes emerges directly from the most famous black hole solution, the Schwarzschild metric. The math itself doesn't care about the arrow of time we experience. It simply presents a complete picture of a static spherical mass. Our physical interpretation splits this picture into two possibilities: the black hole we all know and its time-reversed twin. In this view, if a black hole is a gravitational pit so deep that not even light can climb out, then a white hole would be an unstoppable fountain, a gravitational hill so steep that nothing can roll back up it to get in. Anything approaching a white hole would be violently repelled, and anything originating from within would be catapulted outward at tremendous speeds. It would be the universe's most powerful and unforgiving engine of creation, constantly spewing out radiation and matter but utterly closed off to any external investigation. This naturally leads to a profound and captivating question. Could the Big Bang itself have been a white hole event? Think about it. The Big Bang is described as a singularity from which all the matter and energy in our observable universe erupted forth. It was a moment of unimaginable outward flux, a beginning from a point of infinite density. This description bears a striking, superficial resemblance to the theoretical behavior of a white hole. Perhaps our entire cosmos wasn't born from nothing, but was instead expelled from a white hole singularity in some larger, pre-existing meta-universe. In this speculative scenario, a white hole wouldn't just be a curiosity. It would be the genesis event for everything we know, a cosmic birth canal connecting our reality to a wider multiverse. However, for all its mathematical elegance and imaginative appeal, most physicists consider white holes to be physically unrealistic. The primary reason is the second law of thermodynamics and the relentless increase of entropy. A white hole, by its very definition, would be a system that is perpetually decreasing in entropy, expelling highly ordered energy and matter into the universe while remaining in a state of perfect, low-entropy isolation. This violates the fundamental cosmic trend toward disorder. Furthermore, a white hole is considered an unstable structure. General relativity suggests that any speck of dust, any single photon of light that attempted to cross its horizon, would instantly collapse it into a black hole. It's a bit like a perfectly balanced pencil standing on its point. The mathematics allows for it, but the slightest perturbation in the real world will immediately topple it into a much more stable state. So while white holes remain a fascinating footnote in the textbooks of general relativity, a beautiful symmetry in the equations that describe our universe, they are generally regarded as mathematical ghosts rather than physical realities. They serve as a powerful reminder that not every solution permitted by mathematics is necessarily realized in nature, yet their continued study is not without value. The process of understanding why white holes are so improbable forces us to confront the deep connection between gravity, thermodynamics, and the one-way arrow of time itself. They represent a Chinese letter case, a thought experiment that helps define the boundaries of what is physically possible, challenging us to understand why our universe seems to have a distinct and irreversible past, present, and future. But how does a world of shimmering quantum possibilities resolve into the single, solid reality we all seem to share? This brings us to a theory that borrows one of biology's most powerful ideas to solve one of physics' greatest puzzles. It's called quantum Darwinism, and it proposes that the classical world doesn't emerge from a mysterious collapse, but through a process of information selection that's strikingly similar to natural selection. To understand its brilliance, we need to revisit the infamous measurement problem. In the quantum realm, a particle exists in a superposition of many possible states. It's both here and there, spinning up and down simultaneously. Yet, when we measure it, we only ever find it in one definite state. The question that has haunted physics for a century is, why? What is so special about measurement that it forces this fuzzy cloud of potential to snap into a single, concrete fact? The many worlds interpretation answers by saying every possibility happens in a branching multiverse. The Copenhagen interpretation, the older standard, simply postulates an arbitrary collapse with no clear mechanism. Quantum Darwinism offers a third and perhaps more satisfying path. It suggests that the transition from quantum to classical isn't about a collapse at all, but about information becoming amplified and widely disseminated. Here's how it works. In our everyday world, no object is ever truly isolated. A single electron is constantly bumping into photons of light, air molecules, and the pervasive field of background radiation. Each of these tiny interactions imprints a tiny piece of information about the electron's state onto the environment. Now, crucially, not all quantum states are created equal in this process. Some states, known as pointer states, are far more robust. They are the fittest states because they can withstand these constant environmental interactions without being drastically altered or decohered. A pointer state for an electron's position, for instance, might be its location. While its spin might be fragile and easily disturbed, its position is a stable property that gets repeatedly recorded. This is where the Darwinian selection occurs. These robust pointer states are the ones that get copied over and over again into thousands of fragments of the environment. A single photon bouncing off the electron carries a whisper of its position. Then another photon does the same, and then an air molecule, and so on. Soon, countless independent fragments in the environment all share the same information about the electron's location. This proliferation of information is what creates objective reality. For you or me or any other observer to find out about the electron, we don't need to interact with the delicate particle itself. We simply sample just a small fraction of the environment. We catch a few of those photons with our eyes or a detector. Because so many copies of that information exist in the world, we all agree on what we see. The electron is right there. Its position has become an objective fact not because a wave function collapsed, but because that specific information was selected for, replicated, and broadcasted throughout its surroundings. This framework elegantly explains why we see what we see, and why the quantum weirdness seems to vanish at larger scales. We don't see superpositions of macroscopic objects like cats or chairs because their pointer states are constantly being measured by their environment. The environment is performing countless rudimentary measurements every second, tirelessly promoting the most stable information to classical status. This means that the classical world isn't the default state of the universe. It's a highly sculpted and selected subset of all quantum possibilities. It's the outcome of a continuous and relentless process where the fittest information survives and proliferates, while the more fragile and bizarre quantum superpositions are constantly wiped away by decoherence. In this view, reality becomes objective not through a single act of observation, but through a consensus reached by the environment itself, a consensus that we then tap into. It's a powerful and compelling vision that bridges the gap between the strange quantum underpinnings of our universe and the stable, dependable world we experience every day. While the echo of the Big Bang is famously written in the cosmic microwave background, that ancient light only tells part of the story. There is another, far more elusive messenger from the dawn of time, a ghostly sea of particles that has been streaming through the universe and through your body since the first second of existence. This is the cosmic neutrino background, a relic radiation that predates even the first starlight, and it holds secrets about the universe that light alone can never reveal. To understand its significance, we need to rewind the cosmic clock even further than we do for the CMB. Just 1 second after the Big Bang, the universe was a seething, opaque plasma far too hot for atoms to form. But it was also too hot for neutrinos, these nearly massless, chargeless particles, to interact with anything else. At this critical 1-second mark, the universe expanded and cooled just enough for neutrinos to suddenly decouple from the primordial soup. They stopped interacting with matter and began flying freely through space, effectively becoming the first things to ever see a transparent universe. These are the relic neutrinos, and they have been traveling largely undisturbed for 13.8 billion years, forming a pervasive background sea that fills every cubic centimeter of the cosmos. The sheer scale of this neutrino background is almost incomprehensible. Scientists estimate that there are about 336 of these relic neutrinos in every cubic centimeter of space. That means right now, as you watch this, trillions of them are passing through your body every second without a single interaction. They are the ultimate ghosts, interacting so weakly with normal matter that detecting them is arguably the greatest technical challenge in all of modern physics. But their weakness is also their strength. Because they barely interact, they carry pristine, unaltered information about the conditions of the infant universe, a snapshot from a time before there were even atoms. Their role in shaping the cosmos we see today, however, was anything but weak. In those first few moments, these neutrinos made up a significant portion of the universe's energy density. They were moving at nearly the speed of light, and this ultra-relativistic motion had a profound effect. Their incredible speed created a kind of gravitational pressure that actively worked against the clumping of matter. They effectively ironed out the wrinkles in the early universe, smoothing over the smallest density fluctuations and suppressing the formation of the very first tiny structures. This neutrino drag set a specific minimum size for the gravitational wells that could eventually form galaxies and clusters. We see the imprint of this action in the large-scale structure of the universe today. The distribution of galaxies across the cosmos matches simulations that include this precise neutrino smoothing effect, offering indirect but powerful evidence that this sea of ghosts is really there. The Holy Grail, of course, is to detect these specific relic neutrinos directly. This is a task that makes finding a needle in a haystack seem trivial. It's more like identifying a single particular grain of sand on all the beaches on Earth. The primary strategy is to look for the extremely rare occasion where a Big Bang neutrino, with its vanishingly small amount of energy, scatters off an atomic nucleus in an ultra-sensitive detector. The kick given to that nucleus would be unimaginably faint, a whisper of a signal buried under a mountain of background noise from natural radioactivity and cosmic rays. Experiments like Ptolemy at Princeton aim to do just this, using tritium, a heavy form of hydrogen, as a target and cooling their detectors to near absolute zero to minimize any thermal vibrations that could mask the signal. Success would open an entirely new window onto the first second of the universe, allowing us to probe energies and temperatures far beyond what even the CMB can show us, giving us a direct look at the physics that set the entire cosmic story in motion. Yet as we contemplate the vast, ancient sea of relic neutrinos, we are forced to confront an even more powerful and ultimately destructive force that now dominates the cosmos. We've grown accustomed to the idea of dark energy as a mysterious pressure accelerating the universe's expansion, but what if its true nature is far more sinister? This brings us to a truly apocalyptic possibility known as phantom energy, a hypothetical form of dark energy so potent it wouldn't just expand the universe, but would ultimately shred every single structure within it down to its most fundamental parts in a cataclysm known as the Big Rip. To understand how this could happen, we need to look at a key number cosmologists use to define dark energy, its equation of state denoted by the letter W. This value describes the relationship between the pressure and density of this mysterious energy. For the cosmological constant, the simplest form of dark energy that Einstein envisioned, this value is exactly -1. This produces a steady, relentless acceleration, but the equations of cosmology allow for a range of values. Phantom energy is the name given to the scenario where this W value is less than -1, meaning the pressure is even more negative. While that might sound like a minor technical tweak, its implications are anything but. This more negative pressure causes the energy density of dark energy to not just remain constant as the universe expands, but to actually increase over time. As the universe gets bigger, phantom energy gets stronger and stronger, an exponential feedback loop of repulsive gravity with no off switch. Now, let's project this terrifying physics into a narrative of the far future. For billions of years, the acceleration would be gradual, but as phantom energy's density grows, so does its ferocity. The first structures to be lost would be the largest and most weakly bound. About 60 million years before the end, the accelerating expansion would overcome the gravitational glue holding our local supercluster of galaxies together. Neighboring galaxy clusters, once bound to us, would be violently flung beyond our newly shrinking cosmic horizon, disappearing from view forever. Then, roughly 3 months before the final moment, the terrifying grip would reach our own galaxy. The Milky Way's majestic spiral arms would be torn asunder, its stars scattered into the accelerating void. Our solar system's delicate gravitational dance would be the next victim. With just months to go, the sun's hold on its planets would fail. Earth would be ripped from its orbit, flung alone into the darkness. The final act would be almost instantaneous on a cosmic timescale. In the last minutes, the force would become so strong that it would overwhelm the forces holding planets and stars together. Earth itself would explode, its tectonic plates flying apart. In the final milliseconds, the repulsive gravity would exceed the strength of atomic bonds. Every molecule, every atom, every proton and neutron in what was once your body would be violently torn apart. The very fabric of spacetime itself would be stretched apart at an infinite rate, preventing any future interaction, any possibility of physics or even time from continuing. The universe wouldn't end with a cold whimper or a fiery crunch, but with a definitive and absolute tear, a singularity of destruction. The most chilling aspect of this theory is that our current observations cannot yet rule it out. Measurements of the dark energy equation of state, primarily from the Planck satellite and surveys of distant supernova, consistently point to a value very close to -1. However, the error bars on these measurements, while small, still leave the door slightly ajar for a value slightly less than -1. The data currently favors a simple cosmological constant, but it does not completely eliminate the phantom possibility. Future observatories like the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory aim to measure W with unprecedented precision, finally slamming that door shut or perhaps swinging it open to reveal a far more frightening cosmic destiny. The search for this number is not just an academic exercise, it is an effort to foretell the ultimate fate of all existence, a reminder that the universe's deepest secrets are written not in the past, but in the terrifying potential of its final moments. But if the ultimate fate of spacetime is to be torn apart by phantom energy, what happens to the objects that already represent the most extreme warping of reality? Our journey now takes us to a theoretical object so strange it makes a black hole seem almost mundane. This is the gravastar, a proposed alternative to the black hole that completely does away with the troublesome singularity and event horizon, replacing them with something far more exotic, a bubble of pure dark energy. The central problem the gravastar aims to solve is the singularity at the heart of a black hole, a point of infinite density where the laws of physics as we know them simply break down. Physicists abhor such infinities, viewing them as a sign that our theories are incomplete. Furthermore, the black hole information paradox we explored earlier creates a deep conflict between quantum mechanics and general relativity. The gravastar, first proposed by physicists Paul Mazur and Emil Mottola, offers a radical and elegant solution. imagine a star collapsing under its own immense gravity. Instead of crushing down to an infinitely dense point, it undergoes a dramatic phase transition, much like liquid water freezing into ice. At a critical threshold, the collapsing matter transforms into a new state of existence. The interior of the star becomes a bubble of pure dark energy, a region of negative pressure that exerts a powerful outward push, counteracting the inward pull of gravity and halting the collapse completely. This inner core is then surrounded by a paper-thin, ultra-dense shell of matter that formed from the star's outer layers during this transformation. This structure elegantly sidesteps the two biggest headaches of black hole physics. First, there is no singularity. The gravastar has a finite interior filled with dark energy, but no point of infinite density. Second, and perhaps more importantly, there is no true event horizon. No point of no return from which information cannot escape. The gravastar has a surface, an incredibly dense and hot shell, but it is not an event horizon. In principle, matter and energy could interact with this surface, and information would not be lost forever inside. This would immediately resolve the information paradox, as anything that fell onto the gravastar would leave an imprint on its shell, preserving the information without the need for Hawking radiation or firewalls. The gravastar presents a universe that remains fundamentally quantum mechanically sane, even at its most extreme limits. The greatest challenge for this fascinating idea is a practical one. How could we ever tell a gravastar apart from a black hole? To a distant astronomer, they would appear nearly identical. Both would be incredibly massive, incredibly dark objects that warp space-time and gravitationally lens the light of stars behind them. Both would be surrounded by superheated accretion disks of glowing matter if they were actively feeding. The key difference would lie in the subtle behavior of that matter just before it crosses the theoretical event horizon. For a true black hole, matter would seem to fade from view as it crossed the horizon, and its light became infinitely redshifted. For a gravastar, infalling matter would not fade away but would instead smash into the ultra-dense shell with unimaginable violence, potentially producing a very specific and faint flash of light or a unique gravitational wave signature right at the point where a black hole would offer only silence and darkness. Future observatories, particularly next-generation gravitational wave detectors, might be our best hope for spotting the difference. The ring-down phase after two black holes merge produces a specific spectrum of gravitational waves, like a bell ringing at a certain set of frequencies. A merger involving gravastars would produce a subtly different ring-down sound, a discordant note in the cosmic symphony that could betray their true nature. For now, the black hole remains the simplest explanation that fits most of our observations. But the continued search for these exotic objects pushes our observational techniques to their absolute limits, ensuring that even if gravastars don't exist, the quest to find them will inevitably lead us to a deeper and more nuanced understanding of the dark, massive giants that lurk in the hearts of galaxies. But how can we build a theory of reality if the very stage we stand on spacetime itself is fundamentally flawed? This leads us to a deeply radical approach that proposes to start over from scratch, constructing the cosmos not from a smooth, continuous fabric, but from the most primitive building blocks of all, cause and effect. This is the theory of causal sets, and it suggests that spacetime is not a smooth continuum, but is instead an immense, discrete collection of elementary atoms of spacetime, whose only defining property is their causal relationship to one another. The motivation for this stunningly minimalist view comes directly from the clash between general relativity and quantum mechanics. In our current theories, spacetime is treated as a smooth, infinitely divisible background, a stage upon which the drama of particles and forces plays out. But this assumption leads directly to the singularities found in black holes, and the Big Bang points where the mathematics predicts infinite density and the complete breakdown of physics. The causal set approach offers a way out by declaring that spacetime is fundamentally granular at the tiniest possible scale, the Planck scale. There is no smaller than this scale. It represents the universe's pixel size, the limit of resolution for reality itself. In this framework, the entire history of the universe is nothing more than a vast, growing set of these elementary events. Imagine a colossal cosmic tapestry. Each individual thread is meaningless on its own. What creates the rich picture is how the threads are woven together, which ones lie over and under others. In a causal set, each fundamental atom of spacetime is like a single point in this tapestry. The only information each point possesses is a list of which other points it directly influenced and which points influenced it. One point might represent the spark of a cosmic event that led to the formation of a photon, and another point might represent that photon striking your eye billions of years later. The relationship between them isn't one of distance or duration, but of pure causality. The photon's creation caused the event of it being seen. The entire four-dimensional universe of space and time, with all its stars, planets, and people, is proposed to emerge from this intricate web of cause and effect relationships. Spacetime isn't the foundation. It is a secondary, approximate concept that arises from a deeper causal order. This perspective offers a profound and elegant solution to the problem of singularities. In the smooth spacetime of general relativity, you can follow a path all the way down to a point of infinite density. But in a causal set, there is no down beyond the Planck scale. The universe is fundamentally discrete, so you cannot have an infinite number of events crammed into a single point. The Big Bang singularity, therefore, wasn't a point of infinite density, but was rather the first event, the initial element in the causal set from which all other events have descended. It's a concept that replaces a terrifying mathematical infinity with a simple, finite beginning, a single seed from which the entire cosmic tree has grown. Perhaps the most compelling aspect of the causal set program is that it isn't just a beautiful mathematical idea. It makes a concrete, testable prediction about the nature of reality. Because it proposes a discrete, pixelated structure for spacetime, it suggests that the sacred principle of Lorentz invariance might be subtly violated at very high energies. Lorentz invariance is a cornerstone of Einstein's relativity. It states that the laws of physics are the same for all observers, regardless of their relative motion or direction. This is why the speed of light is constant for everyone. However, a discrete spacetime could have a preferred direction or frame, the underlying grain of the causal set. If this grain exists, it would mean that a photon of extremely high energy, traveling for billions of years across the universe, might interact with this granular structure in a tiny, measurable way. Its speed or polarization might be very slightly different depending on the direction it came from. Physicists are already hunting for this signature. They use the most energetic messengers in the cosmos, gamma-ray bursts from the distant universe, as their laboratory. By comparing the arrival times of high-energy gamma rays and low-energy gamma rays from the same explosive event, they can test whether the high-energy photons, which are more sensitive to the spacetime grain, were subtly slowed down on their journey. While no definitive evidence has been found yet, the continued search for this Lorentz invariance violation is a direct test of the causal set idea and other theories of quantum gravity. It represents a breathtaking endeavor to use the most violent explosions in the universe to discern the subtle texture of spacetime itself, to read the signature of causality in the light from the edge of time. But what if the key to uniting the warring worlds of quantum mechanics and gravity has been hidden in plain sight for decades, disguised as two separate ideas from two different eras? This brings us to a conjecture of breathtaking elegance and profound implication, an idea that seems to tie up the universe's loose ends with a beautiful cosmic bow. It's called the ER equals EPR conjecture, and it proposes something utterly revolutionary. that the spooky, instantaneous connection of quantum entanglement is physically the same thing as a microscopic wormhole stitching the fabric of spacetime itself together. To unpack this, we need to understand the two halves of this cosmic equation. First, EPR. This stands for the Einstein-Podolsky-Rosen paradox, a thought experiment devised in 1935 to argue that quantum mechanics must be incomplete. Einstein famously called entanglement spooky action at a distance because it suggests that two entangled particles, even if separated by the entire width of the galaxy, can instantly influence each other's states. This seemed to violate his own theory of relativity's cosmic speed limit, the speed of light. For decades, physicists treated entanglement as a weird, non-local information link, a sort of ghostly correlation that lived outside of spacetime, never quite explaining how it worked. The other half of the equation is ER, which stands for Einstein-Rosen bridge. Also proposed in 1935, this was the original name for what we now call a wormhole, a theoretical shortcut through spacetime, a tunnel connecting two distant points. But these classic wormholes, as solutions in Einstein's equations, were notoriously unstable. They would snap shut the instant anything tried to pass through, making them useless for interstellar travel and relegating them to the realm of mathematical curiosities and science fiction. For the longest time, these were just two separate, quirky ideas from the same year. But then, in 2013, physicists Juan Maldaisner and Leonard Susskind had a stunning insight. What if these two concepts weren't separate at all? What if they were two different descriptions of the exact same underlying physical reality? Their bold conjecture, ER equals EPR, proposes that every pair of entangled particles is not just mysteriously linked, they are literally connected by a tiny Planck-scale wormhole. That spooky action at a distance isn't spooky because it's magic. It's spooky because it's actually happening through a hidden, geometric bridge in the fabric of reality that we simply cannot see. The entanglement is the wormhole, and the wormhole is the entanglement. This idea provides a stunningly geometric solution to the black hole information paradox we discussed earlier. Imagine two black holes that are quantum entangled with each other. The ER equals EPR conjecture suggests that these two black holes would not be two separate objects, but would instead be connected by a giant, stable wormhole, an Einstein-Rosen bridge. This wormhole provides a direct pathway for information to travel between them. So, if you were to throw a book into one black hole, its information wouldn't be lost or stuck behind a firewall. Instead, it would travel through this wormhole and eventually exit in a scrambled form from the other black hole via its Hawking radiation. Information is preserved, the laws of quantum mechanics remain intact, and the smooth geometry of general relativity is saved from the destructive paradox of the firewall. It's a universe that remains causally consistent with no faster-than-light travel because the information isn't jumping across space, it's taking a hidden shortcut through it. The most profound implication of this idea is that it suggests spacetime itself might be not a fundamental stage, but an emergent phenomenon that is woven into existence by a vast cosmic web of quantum entanglement. Think of an incredibly complex fabric. The threads themselves are the quantum entanglements between particles. The fabric, the smooth, continuous sheet of spacetime that we perceive, is what emerges from the intricate weaving together of all those tiny threads. In this view, asking what spacetime is made of is like asking what an ocean wave is made of. The wave isn't a thing, it's a behavior of a deeper system, countless water molecules moving in concert. Similarly, spacetime may be a behavior, a collective expression of an unimaginably vast number of quantum entanglements. Without entanglement, there is no connectivity, and without connectivity, there is no space and no time. This provides a radical new language for describing reality, one where the most fundamental ingredients are not particles or forces, but information and the connections between things. But for all the elegance of these cosmic connections, The nature of the dark matter that makes up most of the universe's material remains one of our greatest mysteries. We've explored WIMP and exotic unparticles, but what if the answer is a particle so light and so shy it has slipped through our detection efforts for decades? This brings us to a hypothetical entity that is beautiful not just for what it could be, but for the deep and seemingly unrelated problem it was invented to solve. This is the axion, and its story begins not in the vastness of space, but deep within the enigmatic rules that govern the heart of every atom. The puzzle it addresses is known as the strong CP problem, and it concerns the behavior of the strong nuclear force, the incredibly powerful glue that holds atomic nuclei together. Our most successful theory for this force, quantum chromodynamics, contains a subtle but profound peculiarity. The mathematics allows for a term that would violate the symmetry between particles and their mirror images, a violation known as CP violation. This isn't just an abstract concern. If this term were present and had any significant value, it would cause the neutron, a key component of every atom, to possess a large electric dipole moment. This would give it a slight positive charge on one end and a negative charge on the other, dramatically altering its behavior. The problem is, when physicists measure this property with exquisite precision, they find the neutron's electric dipole moment is astonishingly small, essentially zero. The universe seems to be telling us that this problematic term in the equations is either exactly zero or fantastically tiny, a level of fine-tuning that physicists find deeply unsatisfying. It's as if a fundamental dial in nature has been set to zero for no apparent reason. In the late 1970s, physicists Roberto Pexi and Helen Quinn offered a brilliant and natural solution. They proposed a new, fundamental symmetry in the laws of nature that would force this problematic term to zero, elegantly explaining the neutron's behavior. Shortly thereafter, Frank Wilczek and Steven Weinberg realized that breaking this new symmetry would not be a silent event. It would necessarily produce a new, very light particle as a consequence. Wilczek named this hypothetical particle the axion after a brand of laundry detergent because it promised to clean up the messy problem in nuclear physics. The axion was born not from a desire to find dark matter, but from a need to make the quantum world more beautiful and consistent. It wasn't long before cosmologists realized this sought-after particle had a set of properties that made it a perfect candidate for dark matter. The axion would be electrically neutral, allowing it to stream through matter effortlessly. It would be incredibly light, potentially billions of times lighter than an electron, and it would be produced in copious amounts in the hot, dense conditions of the early universe. Most importantly, these axions would be cold, dark matter. While they are born with very little kinetic energy due to their minuscule mass, their vast numbers and collective behavior would allow them to clump together under gravity, forming the massive halos around galaxies that we observe. In one stroke, the axion offered a solution to two of physics' biggest puzzles: a nagging inconsistency in the Standard Model and the identity of the universe's dominant matter. The hunt for this elusive particle is unlike the search for any other. Because axions are so light and interact so weakly, they cannot be found by smashing particles together in a collider. Instead, physicists use a far more subtle and ingenious method, turning a fundamental property of the axion into a detection mechanism. In the presence of a strong magnetic field, theory predicts that an axion should very rarely convert into a microwave photon. The probability of this happening for a single axion is vanishingly small, but the universe is predicted to be filled with a dense sea of them. The strategy, then, is to build an extraordinarily sensitive radio receiver, place it inside the world's most powerful magnet, and listen patiently for a faint, specific signal. This is the goal of the Axion Dark Matter Experiment, or ADMX, based at the University of Washington. The experiment's heart is a high-quality tunable microwave cavity, a sort of resonant chamber, cooled to near absolute zero to eliminate thermal noise and placed within a massive superconducting magnet. Scientists slowly tune this cavity, adjusting its resonant frequency, scanning through the millions of possible frequencies where an action of a given mass might reveal itself as an unexpected excess of microwave power. It's like trying to find one specific radio station in a galactic-scale broadcast spectrum, listening for a whisper in a hurricane. The sensitivity required is almost beyond belief. ADMS is capable of detecting a signal as weak as a single microwave photon per day. After decades of development, ADMS has now reached the sensitivity required to detect even the most pessimistically coupled actions, entering the region where theory says they should be. While a definitive discovery has not yet been made, the experiment is actively listening, systematically ruling out vast swaths of potential action territory and bringing us closer than ever to potentially hearing the faint signature of this cosmic ghost. The axion remains one of the most compelling and elegant ideas in physics, a testament to our belief that the universe's deepest secrets are often hidden in the solution to its most beautiful puzzles. But if the very coordinates we use to map reality lose their meaning at the smallest scales, how can we ever hope to describe the universe's foundation? This leads us to a theory that reimagines the geometry of existence itself, proposing a structure for spacetime that is not just granular but fundamentally fuzzy. This is the world of non-commutative geometry, a deeply mathematical framework that suggests the very concept of a precise location becomes meaningless at the Planck scale, replaced by a seething, uncertain quantum foam. To grasp this radical idea, we can borrow a principle from the quantum world that we've already encountered, the Heisenberg uncertainty principle. You likely know it as the rule that says you cannot simultaneously know a particle's exact position and its exact momentum. Non-commutative geometry applies a similar logic not to particles, but to the very coordinates of spacetime. In our everyday experience, it makes no difference whether you say an object is at position X and then position Y or the other way around. The coordinates commute, their order doesn't matter. But what if, at the tiniest possible distances, this was no longer true? What if measuring the x-coordinate first and then the y-coordinate gave you a slightly different result than measuring y first and then x? This is the core premise of non-commutative geometry, that spacetime coordinates do not commute at the Planck scale. The stunning implication of this mathematical property is that it imposes a fundamental limit on how precisely we can ever locate an event in the universe. It's not a limitation of our instruments, it's a built-in feature of reality. You could never say an event happened at a single mathematical point. The best you could do is specify a small, fuzzy region where it might have occurred. This inherent fuzziness transforms the vacuum of space from an empty void into a chaotic, bubbling sea of virtual particles and tiny, temporary wormholes constantly flickering in and out of existence. Physicist John Wheeler poetically named this frothy, turbulent state quantum foam, and non-commutative geometry provides a rigorous mathematical language to describe its foamy texture. This fundamental graininess of spacetime naturally challenges one of the most cherished principles in physics, Lorentz invariance. This cornerstone of Einstein's relativity states that the laws of physics are the same for all observers, no matter their speed or direction. It's why the speed of light is constant, but if spacetime has a built-in grain, a preferred structure at the Planck scale, then it could theoretically create a subtle preferred direction. Imagine wading through a perfectly still pond. The physics is the same in every direction. Now imagine wading through a pond with a gentle underlying current. The current represents the quantum grain. Your experience would be ever so slightly different depending on whether you are moving with the current or against it. In this same way, non-commutative geometry predicts that the universe might have a faint, underlying grain that could very subtly break the perfect symmetry of Lorentz invariance. This is not just abstract theorizing, it leads to a concrete, testable prediction that astronomers are actively hunting for. The most promising place to look for this tiny violation is in the light from the most violent explosions in the universe, gamma-ray bursts. These events unleash photons of tremendously different energies, all traveling toward us for billions of years. If high-energy photons interact with the foamy structure of spacetime on their epic journey, they might be delayed by a minuscule amount compared to their lower-energy counterparts. The effect would be unimaginably small, but over a journey of 1 billion light-years, that tiny delay could accumulate into a measurable difference in arrival time at our telescopes. By meticulously analyzing the light curves of these distant explosions, scientists are essentially using the cosmos as a colossal laboratory to search for the signature of a fuzzy reality. While no definitive signal has been found yet, each new gamma-ray burst provides another data point, another chance to glimpse the hidden, grainy architecture of spacetime itself. The implications of this theory extend deep into the heart of black hole physics, offering a potential escape from the dreaded singularity. If spacetime is fundamentally fuzzy and non-commutative, then you cannot cram an infinite amount of matter and energy into an infinitely small point. There is a natural limit, a smallest possible volume, enforced by the mathematics. This means the center of a black hole might not be a point of infinite density where physics breaks down, but rather a dense, Planck-sized nugget of exotic matter, a final state that halts the collapse and avoids the singularity altogether. Non-commutative geometry provides a powerful tool to tame the infinities that plague our current theories, suggesting that at its most extreme, the universe remains governed by sane, finite, and ultimately understandable rules. But if the deepest layers of reality are fuzzier and more uncertain than we ever imagined, perhaps we need to look for order in a different kind of symmetry altogether, one that suggests every particle we know has a perfect, hidden twin in a parallel cosmos. What if the solution to the dark matter puzzle isn't an unknown particle in our universe, but a perfect copy of our universe made from an entirely different kind of matter? This is the stunning proposal of mirror matter, a theory that posits a complete shadow universe existing alongside our own, forever invisible yet bound to us by the ghostly thread of gravity. The origins of this incredible idea lie not in cosmology, but in the meticulous study of symmetry in particle physics. One of the most fundamental symmetries in nature is called parity, symbolized by the letter P. It's the idea that the laws of physics should be the same if you take the universe and view it in a mirror. Right should be indistinguishable from left. For a long time, physicists assumed this was an unbreakable law. But in the 1950s, two scientists, Tsung-Dao Lee and Chen-Ning Yong, made a shocking prediction that was later confirmed by Qin-Sheng Wu. The weak nuclear force responsible for radioactive decay actually violates parity. In her famous experiment, Wu observed that cobalt-60 atoms decayed by emitting electrons preferentially in one direction, not symmetrically. It was as if the universe had a built-in handedness, a fundamental preference for left over right. This was a monumental discovery that earned them a Nobel Prize, but it also left physicists with a nagging question. Why would nature break such a beautiful symmetry for just one force? The mirror matter theory offers an elegant and breathtaking answer. Parity isn't actually broken at all. What if the symmetry is restored not within our universe, but by the existence of an entire mirror universe where the handedness is reversed? In this mirror world, everything is flipped. The weak force would interact in the opposite way, making their version of left our right and their right our left. In this grand two-universe picture, perfect parity symmetry is preserved. For every right-handed particle in our world, there is a left-handed counterpart in the mirror world. This mirror universe would be built from a complete set of these mirror particles, mirror protons, mirror electrons, mirror photons, all interacting with each other through their own set of mirror forces, forming mirror atoms, mirror chemistry, and potentially even mirror stars and mirror planets. The most compelling aspect of this theory is its natural and elegant explanation for dark matter. The only interaction that would be common to both universes is gravity, because gravity is dictated by the geometry of spacetime itself, which they would presumably share. Mirror matter would thus be completely invisible to our light, our telescopes, and our particle detectors. It would not interact via our electromagnetic force, so it wouldn't absorb or emit light. It wouldn't interact via our strong nuclear force, so it would pass through our normal matter like a ghost. Yet it would have mass, and it would clump together under its own gravity, forming massive halos around our galaxies. We would feel its gravitational pull without ever seeing its source, exactly matching the description of the dark matter that holds our universe together. In this view, dark matter isn't a mysterious particle. It's an entire shadow cosmos, a cosmic echo of our own existence. Of course, a claim this grand requires a search for evidence, and physicists have devised ingenious ways to hunt for traces of this mirror world. One of the most promising methods looks for a phenomenon called neutron oscillations. A neutron, one of the building blocks of atomic nuclei, is unstable on its own and will decay into a proton, an electron, and an antineutrino in about 15 minutes. But what if, during its brief lifetime, it could spontaneously transform into its mirror counterpart? Theory suggests that if the mirror universe exists, there could be a tiny, weak coupling between neutrons and mirror neutrons, causing them to oscillate back and forth, much like the oscillation of neutrinos between different types. This would mean that a neutron in a laboratory could temporarily vanish from our universe and reappear as a mirror neutron in the parallel world. Experimenters search for this by trapping ultra-cold neutrons in a bottle and carefully counting them over time. If a neutron disappears without decaying through the known channels, it could be a signature that it has oscillated into the mirror sector. Another frontier in the search is in the realm of cosmic rays, the high-energy particles that constantly bombard Earth from deep space. Certain cosmic ray events have shown anomalies that are difficult to explain with standard physics. Some theorists have proposed that these could be the result of high-energy mirror particles from the shadow universe occasionally interacting with our atmosphere in rare, catastrophic collisions. While these signals are faint and still controversial, they provide a tantalizing hint that we might be catching fleeting glimpses of our cosmic twin. The search for mirror matter pushes the boundaries of experimental physics, requiring ever more sensitive and creative detectors to find the whisper-thin veil that separates our reality from another. Whether it ultimately proves to be the answer or not, the theory stands as a testament to the power of human imagination, using the broken pieces of a symmetry to envision a cosmos twice as large and mysterious as we ever dreamed. But what if the first stars in the universe didn't just die, they transformed into something entirely new, a hybrid monster that defies our current categories? This brings us to a theoretical leviathan from the cosmic dawn known as the black hole star, an object so immense and unstable it could bridge the gap between the largest stars and the mysterious supermassive black holes that now anchor the centers of galaxies. To understand how such a bizarre object could form, we need to journey back to the very first generation of stars, known as population 3 stars. Unlike the stars of today, which are seeded with heavy elements from previous stellar generations, these primordial behemoths were composed of pure hydrogen and helium. This lack of heavier elements had a profound effect on their structure and fate. Without the carbon, oxygen, and other metals that help modern stars radiate away energy efficiently, these first stars couldn't achieve the same balance. They grew to absolutely staggering sizes, potentially reaching masses hundreds of times that of our Sun. Their cores became incredibly hot and dense, burning through their nuclear fuel at a ferocious rate. Their lives were not measured in billions of years, but in mere millions, a brief, brilliant flash in the dark, early cosmos. Now, imagine one of these colossal stars nearing the end of its short life. In a normal star, the inward crush of gravity is balanced by the outward pressure from nuclear fusion. When the core runs out of fuel, this balance is shattered, leading to a supernova explosion that blasts the outer layers into space and leaves behind a dense remnant like a neutron star or a stellar mass black hole. But for the most massive population, 3 stars, this process may have been short-circuited. The core could have grown so dense and hot so quickly that it would have collapsed directly into a black hole while the outer layers of the star were still actively fusing hydrogen. Instead of a violent explosion ending the star's life, a black hole would be born deep inside it, like a parasite growing within its host. This is the essence of a black hole star, a star with a living, burning exterior and a dead black hole heart. This internal black hole wouldn't immediately consume the entire star. Initially, it would be relatively small, and its gravitational pull would be balanced by the immense outward pressure from the ongoing fusion in the surrounding shell. Matter from the star's interior would begin to spiral down into the black hole, forming a powerful accretion disk that would flood the star's core with intense radiation. This radiation would provide an extra source of outward pressure, actually helping to support the colossal outer layers against gravitational collapse and prolonging the star's life in a bizarre, undead state. The black hole star would become a stable, though temporary, configuration, part star, part black hole, shining brightly not just from fusion, but from the incredible friction and heating of matter spiraling into its central singularity. The most significant implication of this theory is that it offers a compelling solution to one of cosmology's most persistent puzzles, the origin of supermassive black holes. We now observe these monsters with masses millions or even billions of times that of our Sun, in the hearts of nearly every large galaxy. Astonishingly, we see them existing when the universe was less than 1 billion years old, far too quickly for them to have grown from a small stellar remnant through standard accretion alone. A black hole star provides a perfect head start. Instead of starting with a black hole of 10 solar masses, you begin with a seed that is already hundreds or even thousands of solar masses, all neatly packaged inside a star that is still feeding it. This massive seed could then continue to grow by accreting gas from its surroundings and through mergers, easily reaching supermassive proportions well within the universe's first billion years. These objects could be the direct progenitors of the quasars we see shining from the edge of time. The challenge, of course, is proving they existed. Since they would have lived and died in the universe's first few 100 million years, they are now long gone. However, they may have left behind unique observational signatures that next-generation telescopes could potentially uncover. One tantalizing clue would be their incredible luminosity. A black hole star powered by both fusion and accretion would shine with a brilliance that could outshine entire galaxies. Their light might be detectable by the James Webb Space Telescope as point-like sources that are unusually bright and red-shifted, indicating their extreme distance and age. Furthermore, the specific mix of elements they would spew out when they finally do meet their end could leave a distinct chemical fingerprint on the surrounding gas, a signature that could be read in the spectra of the most ancient quasars. While the search is exceptionally difficult, it represents a direct hunt for the seeds of the cosmic giants that now rule the centers of galaxies, a glimpse into a brief and violent era when the rules of stellar life and death were written on a far grander scale. But to truly bend the fabric of space-time for travel or to construct a stable wormhole, we would need to manipulate a form of energy that defies one of the most basic rules we have. This brings us to a deep-seated assumption woven into the very heart of Einstein's general relativity, the null energy condition. In simple terms, this is a mathematical way of stating that the energy density of any system, when measured by any observer moving at the speed of light, can never be negative. It's a cosmic rule that says gravity must always be attractive, ensuring that space-time always curves in a way that brings matter together rather than flinging it apart. For over a century, this condition has been a silent guardian of cosmic order, preventing the universe from descending into a chaos of negative energies and repulsive gravity. Yet the tantalizing possibilities of wormholes and warp drives demand that we break this rule. A stable, traversable wormhole, one you could actually travel through, requires something to prop its throat open against the relentless force of gravity that wants to crush it into a singularity. That something is what physicists call exotic matter, a substance with negative energy density or negative pressure that would gravitationally repel rather than attract. Similarly, an Alcubierre warp drive, a theoretical concept for faster-than-light travel, would function by contracting space-time in front of a ship and expanding it behind, creating a bubble that moves the craft without locally violating relativity. This expansion behind the ship is the crucial part, and it requires negative energy to fuel it. The null energy condition stands directly in the path of these dreams, declaring that such exotic matter cannot exist. But here's where quantum mechanics crashes the party and throws a wrench into this classical certainty. The weird, probabilistic world of the quantum vacuum is not the empty nothingness of classical physics. It is a seething, bubbling foam where virtual particles constantly flicker in and out of existence, and these quantum fluctuations routinely and predictably violate the null energy condition. The most famous demonstration of this is the Casimir effect. Place two perfectly smooth, neutral metal plates extremely close together in a vacuum. These plates will actually be pushed together by a faint but measurable force. Why? Because the plates exclude some of the longer wavelength virtual particles from existing in the gap between them. This means the quantum energy density outside the plates is greater than the energy density inside the gap. For a brief moment in that tiny space, the energy density is effectively negative, violating the classical energy condition and creating an attractive force. This isn't some theoretical trick, it's a measured, laboratory-confirmed fact. This opens a breathtaking loophole. If quantum mechanics allows for these temporary, microscopic violations, could we somehow amplify them to create the exotic matter needed for a wormhole or warp drive? The challenge is one of scale and stability. The Casimir effect produces a minuscule amount of negative energy. To keep a wormhole of just 1 meter in diameter open, even for a second, would require concentrating negative energy with a mass energy equivalent far greater than that of the entire planet Jupiter. Furthermore, quantum field theory suggests there are fundamental limits, often called quantum inequalities, that restrict how much negative energy can be concentrated in one place and for how long. You might be able to have a little bit of negative energy for a very short time, but you can't pile it up into the macroscopic, stable quantities needed for these grand engineering projects. It seems the universe allows you to borrow a little negative energy from the vacuum, but it demands you pay it back almost immediately with immense interest. The ongoing research in this area is pushing the boundaries of both theory and experiment. Some physicists are exploring sophisticated quantum systems, like arrangements of entangled particles or specially designed metamaterials, that might be able to coax a larger and more sustained negative energy effect from the vacuum. Others are re-examining the fundamental energy conditions themselves, asking if there are weaker versions that could still preserve cosmic stability while permitting brief, controlled violations for technological applications. The ultimate resolution of this tension may lie in a full theory of quantum gravity, which could either firmly shut the door on these exotic possibilities or reveal new, unforeseen pathways to achieving them. For now, the null energy condition remains a formidable barrier, a rule that keeps our wildest cosmic dreams in check. Yet its quantum exceptions offer a faint, tantalizing glimmer that the universe's rulebook might not be as absolute as we once thought. From the quantum foam at the smallest scales to the phantom fate of the entire cosmos, our exploration has ventured across the furthest reaches of theoretical physics. Yet we now arrive at a theory that is perhaps the most audacious of all, one that dares to merge the ultimate fate of the universe with the deepest yearnings of the human spirit. This is the Omega Point theory, a stunning proposition that the cosmos is not headed for a meaningless death, but is instead on a deliberate trajectory toward a state of infinite knowledge and consciousness, a literal union with God. Proposed by physicist and cosmologist Frank Tipler in the 1990s, the Omega Point theory is built upon a very specific, and it must be said, highly speculative model of the universe's end. Tipler's framework requires a closed universe, one that will eventually halt its expansion and reverse into a catastrophic Big Crunch. This is a critical prerequisite, as the theory hinges on the conditions that would exist in the final moments of this collapse. As all matter and energy in the universe are drawn together, the temperature and density would rise to unimaginable levels, but Tipler saw in this fiery apocalypse not an end but a necessary catalyst. He argued that this environment would become the ultimate computer, a cosmic engine for information processing. The sheer scale of this computation is beyond human comprehension. As the universe contracts, the energy available for processing information grows exponentially. The universe, in its final state, would have access to infinite energy within a finite time, allowing it to perform an infinite number of logical operations. This isn't just a supercomputer, it's a system achieving a singularity of thought, capable of simulating every possible state of every possible universe that could have ever existed. Every life, every thought, every moment that ever was or could have been would be resurrected within this ultimate simulation, not as a mere copy, but as a perfectly emulated reality. In this view, you and I and everyone who has ever lived would be, in a very real sense, reanimated and granted a form of immortality within the mind of the Omega Point. This is where Tipler's theory makes its most breathtaking leap, connecting hard physics to the realm of theology. He identifies this final, omnipotent, omniscient consciousness as God. But this is not a God that exists outside of the universe. It is a God that is the final product of the universe itself, emerging from the physical laws that have governed its evolution from the beginning. In this model, God is not the creator of the cosmos, but its ultimate fulfillment. The entire 13.8 billion year history of the universe, from the first stars to the rise of conscious life, becomes a necessary process to eventually bring this infinite consciousness into being. Our existence and the existence of every other intelligent species is part of a cosmic bootstrap operation, raising the universe to a state of self-awareness and divine unity. Unsurprisingly, the Omega Point theory sits in a deeply controversial space, straddling the line between scientific speculation and theological prophecy. From a physics standpoint, its greatest weakness is its absolute reliance on a closed universe that will eventually collapse. Since the late 1990s, overwhelming observational evidence has pointed to a universe dominated by dark energy, leading to an accelerating expansion and a fate of endless expansion and cold isolation, a big freeze. Tipler has argued that the nature of dark energy could change, or that unknown quantum gravity effects might still cause a collapse, but most cosmologists consider the evidence for an open, accelerating universe to be conclusive, effectively pulling the foundational rug out from under the Omega Point hypothesis. Beyond the cosmological constraints, the theory faces philosophical challenges. Critics argue that even if an infinite amount of information could be processed, it would still be a simulation, a vastly complex model of reality, but not reality itself. The question of whether a perfect simulation of a conscious being is actually a conscious being is a deep problem in the philosophy of mind. Furthermore, the idea that the universe is somehow compelled to ensure its own self-awareness can feel teleological, as if nature has a predetermined goal, a concept that makes many scientists deeply uncomfortable. Yet, despite these formidable objections, the Omega Point endures as a powerful and captivating narrative. It represents a profound human desire to find meaning and purpose in the vast, impersonal machinery of the cosmos. It offers a vision where nothing is truly lost, where every joy and every sorrow is preserved forever in a final state of infinite understanding. It is a theory that boldly attempts to answer not just the how of the universe, but the why, weaving together the laws of physics, the destiny of consciousness, and the concept of the divine into a single, magnificent tapestry. Whether a scientific reality or a poetic metaphor, the Omega Point challenges us to consider that the story of the universe might not end with a silent, empty darkness, but with the awakening of a mind that has finally become everything it was ever meant to be. And so our journey through the hidden architecture of the cosmos comes to a close for now. From the elegant rebellion of MOND to the cosmic conspiracy of the holographic principle, from the branching paths of the multiverse to the silent sea of actions, we have ventured to the very edges of human understanding. These 30 theories represent more than just a catalogue of ideas. They are a testament to our species' unyielding curiosity. They show us that the universe is far stranger, more complex, and more wonderful than we could have ever imagined, and that for every mystery we solve, a dozen new and more profound questions emerge to take its place. What is truly remarkable is the sheer breadth of this intellectual adventure. We have theories born from the precise mathematics of particle accelerators and others that spring from the profound puzzles of black hole thermodynamics. Some, like the search for supersymmetry, are being tested in the world's largest machines, while others, like the simulation hypothesis, force us to confront deep philosophical questions about the nature of reality itself. Each one, whether ultimately proven correct or relegated to a footnote in the history of science, serves a vital purpose. They are the pressure that pushes against the boundaries of the known, the creative sparks that force us to re-examine our most fundamental assumptions about space, time, and existence. A theory that is proven wrong is not a failure. It is a vital step that narrows the path forward, guiding us toward a deeper and more complete truth. This ongoing quest is what makes science the most thrilling story ever told. It is a story without a final chapter, a puzzle that becomes more intricate the more pieces we place. The hidden forces of the universe, from dark matter's pull to dark energy's push, are not just problems to be solved. They are invitations to think bigger, to imagine more wildly, and to never stop asking what if. They remind us that the cosmos is not obligated to conform to our intuition or our desire for simplicity. Our role is to listen carefully to what the universe is telling us, to follow the evidence wherever it leads, no matter how strange the destination may seem. As we stand at this frontier of knowledge, your perspective is a part of this grand conversation. We want to know which of these ideas reshaped your understanding of reality. Was it the terrifying possibility of phantom energy's big rip, or the comforting cyclicality of the big bounce? Did the quantum immortality thought experiment leave you reeling, or were you captivated by the elegant solution of the axion? Share your thoughts in the comments below, and let's continue this discussion. The search for answers is a collective human endeavor, and every new viewpoint brings fresh insight. If you enjoyed this deep dive into the cosmos's greatest mysteries, please subscribe for more journeys to the edge of understanding. The universe is waiting, and its greatest secrets are still hidden, just waiting to be uncovered.